NASA's latest robotic lander, InSight, descends to the surface of Mars. A challenging effort greeted with elation.
Touchdown confirmed.
Meanwhile, an orbiting ESA satellite, ExoMars, begins its own exploration of this enthralling planet. The majestic stereo imagery of Mars as seen from orbit reveals a planet of dynamic texture and form, slowly revealing its secrets.
We've sent a lot of missions to Mars in the past. We've sent rovers, we've sent orbiters, they've done a lot of really great science and a lot of really interesting measurements, but those measurements just scratch the surface of Mars. We know a lot about the surface of Mars, we know a lot about its atmosphere, and even about its ionosphere, but we don't know very much about what goes on a mile below the surface, much less 2,000 miles below the surface down to the center. And this will be the first mission that's going to Mars specifically to investigate the huge extent of Mars below the surface. The basic idea of InSight is to map out the deep structure of Mars for the very first time. We're going to map out the thickness of the crust, the size of the core, the composition of the mantle and core of the planet, sort of get the first map of the deep inside of Mars. It's going to Mars to do the science, to make the measurements that scientifically and personally I've been waiting for over 30 years for. As a graduate student, I was doing research on Mars, and I just needed to have the thickness of the crust. I just needed the thickness of the crust, and we didn't have it. And seismology was the way to do it. And so I thought, well, maybe someday somebody will put a seismometer on Mars and get this measurement so I can do my research. And so it's kind of an amazing journey for me to look back and say, I'm the guy who's actually going to put that seismometer on Mars, get that information, and now I can go back and finish the job I was trying to do 30 years ago. It's an amazing feeling.
The InSight mission will finally provide seismic information of Mars that scientists have been wanting since the very first Mars lander, Viking. It had a seismometer on it, but for a variety of reasons it never got back any seismic data. There's been many other attempts to get seismometers onto the surface of Mars for very good science reasons, but they've, for one reason or another, never been successful. So now we're right on the very edge of getting a seismometer onto Mars that will finally give us back seismic data. That seismic data is incredibly important to scientists because it gives them an idea of what the size of the crust, the mantle, and the core are, as well as the properties of each of those, which are the basic internals of every rocky planet.
I think that's an interesting thing.
This one piece will make 52 layers.
Watch
on mobile devices or the big screen. All for free. No subscription required.
The most fun or interesting thing about Insight from an engineer's point of view is really that we're playing the claw game super far away on Mars. We're taking this grapple and we're going to pick up an instrument and lift it up off the deck and put it down on Mars. So I like to say that we're playing the claw game on Mars with no joystick.
Next, a wind and thermal shield will be lowered over the seismic instrument to protect it from the environment. The second instrument, the heat flow probe, will be placed on the ground and over time will hammer itself down to take subsurface readings.
There's a lot of international partners on InSight. It really takes a whole world to produce an exciting mission like this. So most of our science missions are actually being supported by our international partners. So for example, the SEIS instrument, our seismometer, has support from the French, the Germans, the Swiss, the UK folks. So we have a variety of those people. The heat flow and physical properties probe is being provided by the Germans with some support from Poland.
InSight is a mission to Mars, but it's much, much more than a Mars mission. In some sense, it's like a time machine. It's measuring the structure of Mars that was put in place 4.5 billion years ago, so we can go back and understand the processes that formed Mars just shortly after it was accreted from the solar nebula. By studying Mars, we'll be able to learn more about Earth, Venus, Mercury, even the Moon, even exoplanets around other stars.
ESA's Trace Gas Orbiter mission arrived at Mars some time ago. Since then, this 3.5-ton spacecraft has been gently brushing the atmosphere to gradually adjust its orbit. In ESA's Planetary Missions Control Room in Darmstadt, Germany, flight controllers have been checking systems and commissioning instruments on the ExoMars Trace Gas Orbiter. Now it's ready to begin its science mission.
It has been a long time since we arrived at Mars in October 2016, and we have had a long, very long period, 1 year, of aerobraking, which consisted in reducing the orbital period from the time when we arrived, where it was actually several days, to 2 hours, which is the nominal period for science observations. I'm looking forward to the next few months enormously because the TGO will finally be able to show its full capability, the full capability of its instruments in terms of accuracy and the quantity and quality of data, pictures, spectra. And also because we will be able to do joint observations with our previous spacecraft at Mars, Mars Express, which is still alive and working after 15 years, actually. And for ESA, having 2 spacecraft around Mars in complementary orbits from a scientific point of view is very exciting and will allow certainly some very interesting discoveries and observations.
ExoMars will fill a double role when its partner rover is dispatched to Mars in the coming months in the search for life on the dusty planet.
It is a communication satellite on top of being a science orbiter. The so-called relay function allows us to communicate with all landers and rovers on the surface of Mars. At the moment, there are only rovers and landers from NASA, Curiosity and Opportunity. Some tests had been done already soon after arrival at Mars. And now we are going to start a campaign to calibrate and determine the best performance to relay data.
The Trace Gas Orbiter's primary mission, however, is to identify gases in the Martian atmosphere, particularly methane. First hinted at by Mars Express, and then by NASA's Curiosity rover as it sniffed the atmosphere with special sensors.
Well, we know that the lifetime of methane is very short, just a few hundred years. It will be broken down by the sunlight, by the UV ultraviolet component of the sunlight. So if it is there now, we know that it has to be refilled all the time. And where does it come from? That's the big question. It cannot be synthesized really in the atmosphere. It has to come from the surface or from the subsurface. But what are the processes that produces it? This is what we want to find out. One possibility is that it is some geological reaction between minerals and water. Another possibility is that actually are some microbes down buried underneath the surface that is producing it today or has produced it a long time ago, and they're all dead now, but that the methane has been kept underground and with some mechanism is released to get up into the atmosphere. So these are all these kind of things we try to find out.
By using the orbiter's powerful spectrometer, scientists hope to discover whether the methane comes from a geological or biological source. 95% of methane on our own planet comes from living organisms. The ExoMars rover, landing in 2021, will drill up to 2 meters beneath the surface to search for this evidence of life. And the rover, as well as NASA rovers and landers, will use the orbiter to keep in touch with Earth. Mars exploration is an international endeavor, and every mission adds to our understanding of this alien world, a place that some of us might someday call home.
Planetary exploration is always very exciting, but Mars, of course, has this very special thing, is that there is actually a place that you can imagine yourself walking on. You eventually, within not too far in the time in the future, surely people will be walking on Mars. And that makes it very exciting. And then to think about this idea that there might have been some kind of life or even exist today underground on Mars, that makes it a very special place.
Curiosity landed in Gale Crater on an ancient lake bed. A few months after arrival, it drilled into sedimentary rocks and detected traces of organic molecules using an instrument called SAM.
Well, the SAM instrument detected a variety of organic molecules in a sediment that is from an ancient lake bed in the middle of Gale Crater. And what's important about these is that we now have a lot more certainty that there's organic molecules preserved at the surface of Mars. We didn't know that before. But what's interesting is that we don't know what the source of these organic molecules is right now. There's just not enough information from that. However, if we drill deeper and we look around a little bit more, we might actually be able to get to that information and tell, did they come from life? Did they come from geological processes? Or maybe they were from meteorites that were deposited in the lake. We just don't know right now, but hopefully we'll figure that out.
Curiosity is searching for carbon-based organics.
SAM made the new detections by heating samples of crushed rock to very high temperatures, above 1,000 degrees Fahrenheit. This vaporizes samples and released several species of small hydrocarbons like benzene and propane. Because the hydrocarbons were released at such high temperatures, they may be the fragments of bigger, heavier molecules within the rock similar to kerogens. On Earth, kerogens are found in rocks like black shale and coal and are the products of ancient plant and bacteria.
Some other organics have been detected, like thiophene, which contains sulfur. Introduced by geological processes, this sulfur acts as a preservative, binding organic molecules together and making them resistant to oxidation, so preserving them for millennia.
Organic molecules could be the food for life, or they could be the product of life, or maybe they're from something altogether different, such as geology or meteorites that were deposited into the lake. We don't know what the source is, but there's a story there, and we're going to uncover what that is.
Scientists still don't know if the discovered organics on Mars are biological in origin, but it's exciting to find such old material preserved right at the surface. This finding is also encouraging for future exploration. So for a time, Curiosity continued to travel, find interesting outcrops, drill holes, take samples. Then, inexplicably, something went wrong.
The drill's feed mechanism, which is responsible for moving Curiosity's drill bit into and out of rocks, didn't move when commanded. When Curiosity drills into a rock the way it was designed to, the drill's two stabilizer posts touch the rock first to steady the arm while the drill's feed mechanism moves the bit forward into the rock. Without the feed mechanism working, we can't drill that way. To solve this problem, we do what we always do. We worked it out in the test bed using Curiosity's twin on Earth. Our team of engineers and scientists have been working for months to figure out a way to collect and deliver rock samples without using the feed mechanism. Here's what we came up with. Using our new technique called feed extended drilling, the stabilizers are not used. The bit is now in a forward position extended past the stabilizers. Moving the drill straight into a rock and retracting safely without the stabilizers is challenging. We move the arm instead of the feed mechanism to place the bit onto the rock and press it forward as it drills. After making contact, we apply a light preload and drill a shallow pilot hole. We use a force sensor in the robotic arm to give Curiosity a sense of touch. This lets Curiosity adjust its arm motion and avoid getting stuck while drilling, kind of like you might adjust your arm while drilling into a wall at home. After drilling, we use a similar technique to retract from the hole without getting stuck.
With Rover 2020 design and construction well underway, engineers will be sure to avoid such a problem with Curiosity's cousin, which will land in the Jezero crater in 2020. "2020 will be a banner year for the exploration of Mars. In addition to the launch of NASA's Mars 2020 rover, the European Space Agency and Roscosmos are sending the ExoMars rover to the Red Planet. Rover 2020 and its companion helicopter will no doubt expand our search for life, past or present. However, the big advance forward in organic analysis will be the game changer. Both rovers will carry on board a MoMA.
The Mars Organic Molecule Analyzer, or MoMA, is the largest and most complex instrument on the rover. Its mass spectrometer subsystem and its main electronics were built and tested at NASA's Goddard Space Flight Center, which also contributed mass spectrometers to NASA's Curiosity rover and Maven orbiter. MoMA is designed with a mix of proven hardware and innovative new technologies. Here's how it works. In gas chromatograph mode, crushed Martian rock is put into an oven and heated to 900 degrees Celsius in just 2 minutes, vaporizing the sample. Molecules of hot gas rise up and flow into a narrow 20-meter-long tube. Special coatings inside the tube cause molecules with certain chemistries to slow down more than others, separating the mixture of molecules over time. Next, a beam of electrons ionizes the molecules, giving them a positive electric charge and deflecting them towards the linear ion trap. The ions are caught by a fluctuating electric field and sent to a detector to determine the chemical makeup. While gas chromatography has been used to study Mars since the Viking program, MoMA has a second method for preparing samples that has never been used on another planet. In laser desorption mode, a sample is placed beneath a powerful ultraviolet laser. A beam of energetic light builds within the laser and fires in a billionth of a second, concentrating its energy onto a spot smaller than a grain of sand. This rapidly vaporizes a portion of the sample, releasing large organic molecules that could be broken down by oven heating. The laser shot also ionizes some of the molecules, allowing the vapor to head directly to the linear ion trap. Neutral molecules are ejected by a vacuum, while the remaining ions are sent to the detector to determine their chemical makeup. Laser desorption will enable MoMA to detect long molecules, like lipids, the building blocks of cell membranes, a leap forward in the search for life on Mars.
The question of life on Mars is among the most important in planetary science, and the evidence may be buried just below the surface. With the help of MoMA, we will take one step closer to uncovering the answer. These images will pave the way to a new understanding of life in our solar system. CubeSats. They've been around for a while now. The domain of universities and institutions wanting to teach and gain experience in space. They're low cost, light, and very adaptable. Not only that, but they're also easy to send into orbit. Now, business is eyeing off these microsatellites with big plans for the future. The traditional satellite is an industrial and technological marvel. Designed and built from the ground up for a specific purpose with a long life expectancy, some communications and global positioning satellites are built on an off-the-shelf platform design to help alleviate costs. Launching them into orbit, however, is no easy feat. Weighing as much as 50 tons, they have to be placed in a geosynchronous or high polar orbit, which requires expensive launch facilities. The CubeSat satellite, or microsatellite, devised as a training and development tool for university students, has now taken on a life of its own as a low-cost alternative to the conventional satellites in particular roles and for new purposes not previously considered.
A CubeSat is a nanosatellite basically in a box size. Standard dimensions of a CubeSat would be 10 by 10 by 10 centimeters, and you can have multiples of that unit. So you could have a 3-unit CubeSat, for instance, 10 by 10 by 30 centimeters, and all of the satellite equipment has to fit inside that box. The origin of CubeSats goes back over 10 years. In the US, university professors were looking for ways to allow their students to essentially build and fly satellite hardware during their degree courses. And so that was envisaged as a very low-cost way for universities to get their students well educated in the engineering skill.
University student teams from around Europe have been busy in the last months making the final preparations for ASIO, the European Student Earth Orbiter. ASIO is preparing the space workforce of tomorrow. The student teams designed, constructed and tested the essential parts for the mission.
During its whole project life cycle, ASIO engaged several hundred students, and already before launch we can say that it achieved all its main educational objectives.
Launched aboard a SpaceX small satellite-dedicated Falcon 9, ASIO was released into a polar orbit. Aboard the satellite there is a radio amateur communication system by the University of Surrey and AMSAT UK in the United Kingdom. This enables ASIO to transmit real-time data to schools and universities for science and engineering lessons.
I participated in the LMP project. It is a bit personal project for me because there is a component which I have in the design, and I wrote my thesis from this component.
I've been involved in the development and testing phases of the power distribution unit of the ASIO satellites. It's an amazing feeling that your device will go up into space and it's ready, it's working well, and I'm so happy.
ASIO is a complex system, and in the end I think it was challenging activity for all the payload teams. We had the chance to stay with them. We had the chance to teach them a few things that typically are not so common in academia.
ASIO gave us the competence to actually build any scientific instruments here in the observatory. It gave us both the competence and also the connections with ESA, and we learned a lot from the projects in order to develop our further missions.
There's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. There's been evidence, and others have seen this, but again, there's never been a satellite dedicated looking down at Earth for these terrestrial gamma ray bursts.
We want to make artificial signals similar to lightning and see what the board does, make sure it's filtering those signals the way we want.
We're going to put it into HDL code and then get it through this chip.
One of the tenets of the CubeSat program is to involve undergraduate students at all levels, from design to building to some of the theory, data acquisition, every aspect of this. So we're really training here the next generation of space scientists, of satellite engineers. as soon as the launch goes up and they know they're a part of that satellite and data's coming in, I mean, that'll be with them throughout their life.
Where else could CubeSats be applied? A major space mission to Mars, InSight, was a perfect opportunity to test out some new technology.
Liftoff of the United Launch Alliance Atlas V rocket.
The Atlas V RD-180 main engine ignites and generates more than 860,000 pounds of thrust.
Flying with the InSight spacecraft to Mars were two CubeSats. Called Mars Cube 1 or MARCO, they were a technology demonstrator and the first use of miniature modular CubeSat spacecraft design in deep space. The pair of briefcase-sized spacecraft, MARCO A and B, were launched on the same rocket as InSight and traveled independently of the main craft. They carried a number of communication and navigation flight experiments. Although NASA emphasized the experimental nature of the CubeSats before the InSight landing, the MARCO spacecraft performed as intended, receiving the UHF telemetry from InSight during its entry, descent, and landing phase, and rebroadcasting it at X-band frequencies received by NASA's Deep Space Network. This vindicated CubeSats as another tool in the exploration of deep space. To top it off, MARCO B managed to take a photo of Mars and transmit it back to Earth as it passed by the planet. The rush to exploit CubeSats is on. Scientists and engineers have begun designing, building, and launching various designs for specific missions and for testing new technologies in space. Rocket launching companies have been quick to respond, developing and flying dedicated launches for the emerging small satellites market. SpaceX and ESA's Vega launchers are among these companies, while the Electron from Rocket Labs has already begun flying commercial CubeSat launches and is planning a monthly service.
Liftoff
My involvement goes back 10 years from when I was working in the education office at ESA. So indeed, I was responsible for managing university CubeSat projects that we would then later fly on the maiden flight of the Vega launch. We had 7 CubeSats that flew on the Vega maiden flight, and actually many students were involved in those projects, and they went on to graduate, and many of them formed their own spin-off companies, which now forms the basis of the CubeSat industry today. What we're seeing is that the same technologies that are being exploited terrestrially for aerial drones are also being exploited by CubeSats. So I like to think that that same technology will enable CubeSats to become the autonomous drones of the space domain. With the capability of CubeSats to become autonomous space drones, they will have the performance to be able to perform autonomous navigation, close proximity operations around other target objects, and also be able to fly in swarm formations. So these are very advanced architectures. We might also see them being able to perform autonomous rendezvous and docking together, forming building blocks to build up larger structures in space in the future. When we do the CubeSat projects, of course, the standard engineering approach combined with the access to ESA facilities and technical know-how gives an added value to ESA member states to ensure that we maximize the probability of mission success within the tight financial constraints of each project. So far, we've flown one technology CubeSat in orbit, GOMX-3. That mission has been very successful. It's recently re-entered the atmosphere, so the mission has been completed successfully. Now we are preparing to fly another CubeSat called Carmen. It's designed to demonstrate re-entry technologies, a very exciting and challenging project. And beyond that, we have another 4 technology CubeSats in development, and we're already talking to our member states about starting many new projects in the future for these technology demonstrations.
The use of microsatellites for commercial and industrial purposes is a growing field of interest, as is the concept of the Internet of Things. One company has combined the two into what may become the next great technological revolution. Alongside household names like Microsoft, Google, and SpaceX, you may soon be adding Fleet to the list.
So Internet of Things is a concept that probably started 5 to 10 years ago. You know, people were talking about this. There are 25 billion devices coming online in the net. It's the 4th industrial revolution. Everything will be connected. It's going to change our lives. I kind of separate the concept in 2. The smart cities. So when our life will change into buildings, you know, your Fitbit connected to your fridge and your car driving itself, and smart fridges, smart traffic lights, and so forth. And also smart industry. So what happened in remote areas, in a big farm or in a big oil and gas company, a big mining, that's a heavy industrial revolution. So Internet of Things is the idea that we are kind of changing the way we operate. We have spent 40 years connecting people and, you know, bringing computer inside factories, and suddenly everyone has got a computer that cannot live without it. You know, if there's a day you cannot use a computer, you go home because what am I supposed to do? So in the next 40 years, things will change the industry in the same way the computer did. So imagine a big farm suddenly everything will be connected, from the soil to the literally soil, content to animal tracking, weather station, thousands of sensors that we allow the farmer to literally understand so much of the way they operate that we will solve the biggest problem on earth, water leakages and drought and so forth. But that goes into, transport and logistics, not measuring pallets and fruits traveling all over the world. I think we waste 60% of our food in supply chain. So there are big changes happening, and this is all about little sensors being connected. The problem is that this big industry that I'm mentioning, they have no 3G. I mean, 3G, 4G, even 5G covers the population, but 95% of the world is unconnected. And this is where our farms are, where our mining and oil gas company are, where the shipping containers are. So it's a kind of a problem that terrestrial infrastructure cannot solve. And well, we got space, or we solve it from space.
The potential for a constellation or swarms of CubeSats to become powerful research and communication tools is now starting to be explored. The ability to track almost anything across the planet is now a reality. The possibilities seem almost endless.
Internet of Things is interesting because with one satellite in LEO, so low Earth orbit, you cover almost every side of the planet. And customer sees you once a day. It's not much. It's not really good for high-speed internet or talking Skype or checking YouTube, but it's great, for a valve, or a soil moisture sensor, or a cow. You don't want to know where a cow is every single minute of your day. Probably you do, but once a day is perfect for LEO. But when you reach 100, or for us it's 100, it probably will be even less, the latency is so good that you can actually tackle some high pressure emergency applications, like safety and security, in which you want to send the data and grab it straight away and send it to the customer straight away. But the good things of Internet of Things is that you launch one satellite and then you're in operation. You can serve everything now. So we had launched 4 satellites last year. It was a great journey of fleet. For a startup, we launched them in 24 days. 2 with Rocket Lab was first Rocket Lab launch of nano satellites was commercial. So it was literally like, what is going to happen here? And then of course SpaceX and PSLV. But the first satellites we built was almost 1 year. The second one 2 months. When we launched with Rocket Lab, by the time we started building the satellites, to the time we booked the flights and the time we were in space, was 4 weeks. So there's a big revolution also on the launcher side, that can put us in space quite fast.
This startup company seems to have hit the nail on the head. Low-cost terrestrial sensors can be hooked up to almost anything, and their status uploaded to the CubeSats for transmission to the clients via the net.
The people that are booking these sensors, they come from the biggest oil and gas company in the world with all the farms in South America. This is big customer. So we are entering a phase in which, as most startups are starting so little, is having massive customer impact. That satellite company that operates for $1 billion in many, many years don't have. So it's time to see at these satellites and understand it's not a game anymore. This is going to be $1 billion companies very, very fast. So it's quite exciting.
This system could increase efficiencies and save waste across the globe.
Earth needs help. Earth needs monitoring. Earth needs efficiency. Earth needs water to be saved and food to be not wasted and people to be safe. So millions of sensors going to change the world forever. It's going to be billions. When we started Fleet, we started with a dream of connecting the entire world and millions of devices. We call it 1F. It's our first constellation, and For us, 2F is going to be the Moon and 3F is going to be Mars.
The potential for space exploration is exciting. Quick and efficient data networks dispatched to the Moon, Mars, and beyond, or even swarms of CubeSats surrounding an asteroid or a spacecraft during rendezvous, sending back data and video. The scope is limitless.
Imagine you can have a constellation to track every robot and things just to make sure where they are, and this is just the beginning. You know, and the reality is that when the big entrepreneur will go to Mars, they will put so many things, and you want to make sure they're tracked, and it's a complicated exercise. And a CubeSat, it's a way to go there fast. You know, when you need to move a big satellite to Mars, it takes a long time, and you launch a storm of bees. Eventually, they will get there. But eventually, we'll go there, and we will have to do the same. You know, we will have to have big responsibility when we start conquering the other planets, monitoring what happened. I think, yeah, it's going to be fleet responsibility as well, I guess.
The orbit between us and our star, hidden within the sun's glare, often visible only at sunrise or sunset. Venus, the first and brightest star in the evening sky, and Mercury fleeting across the solar disk. They are half of our solar system's terrestrial planets, yet we know so little. As we begin to take a closer look at our companions, they are posing more questions than answers. This is Mercury, the innermost planet closest to our Sun. Mercury's days are longer than its years, and it has an elliptical orbit from 47 million kilometers at its closest point to 70 million kilometers. Difficult to observe from Earth due to the Sun's light, Mercury is an enigma of the solar system's evolution.
Well, Mercury is really a weird planet. Normal terrestrial planets, all the rest, have a relation between how big they are and how dense they are. Mercury is not following that rule. It's much more dense than what you would expect for its size. That is not normal, so something went wrong in the formation of Mercury that we don't know.
Only 2 probes have been sent to investigate the planet, and only 1 has achieved orbit. Mercury is difficult to get to because of its orbital speed and the gravitational influence of the Sun.
Mercury, for us, is a planet of extremes. So you have temperatures like 400, 450 degrees on the surface during the day, and imagine that's like being in a pizza oven on Earth. So it's really hot there, and temperatures at about minus 175 during the night.
Mercury orbits the Sun every 88 days in an atypical elliptical orbit. At its nearest approach to Earth, it is 77 million kilometers away. The first close-up imagery of Mercury came from the US probe Mariner 10 in 1974. With insufficient fuel to slow the craft, it was not possible to put the probe into orbit. Instead, it orbited the Sun, passing by Mercury 3 times. The flybys provided 2 interesting observations. Firstly, Mercury has a magnetic field similar to Earth, which is unusual due to the very slow spin of the planet. Secondly, the surface of the planet showed extensive cratering and very little volcanic or crustal movement, 2 contradictory observations of why the planet has such a magnetic field. The second and most recent probe is Messenger. Launched in 2004, it made several planetary flybys of Earth, Venus and Mercury to slow down to the correct speeds. It took 6.5 years to reach Mercury and enter orbit in 2011.
Because of this short distance from our central star, the temperature of the planet is very, very high. And when you want to fly around Mercury with a satellite, you find yourself in a very special thermal situation where you get a lot of heat coming from the planet itself that behaves like a thermal mirror. And then from the side you get the heat from the sun. So you have two heating sources which may destroy a normal spacecraft. Another NASA mission, Messenger, is getting operational in a very loose Mercury orbit because, as I said, the thermal situation is such that you better stay away from the planet.
Its primary mission was completed within a year, mapping the entire globe with about 100,000 images. With fuel in reserve, the mission life of the probe was extended. After 10 years, Messenger continued to send back information and observations. Magnetic field data, the magnetosphere, the effects of solar wind plasma, and studies of the atmosphere of Mercury. It is so low in density it is constantly blown off the planet as an exosphere, revealing the likes of sodium, calcium, and magnesium in a trailing tail away from the sun. Spectrographic imaging of the surface material has thrown up more questions about the high metallic density of the planet. The observations do not fit the standing theories of the planet's evolution, which will have to be completely overhauled. One other interesting detail: at the north and south polar regions, Messenger has detected the presence of water ice in the permanently shadowed interiors of craters, just like on our moon. In 2014, the probe was tasked to fly much closer to the surface, as close as 50 kilometers. There it imaged the surface at much greater resolution, hunting for more detailed signs of the planet's geological history. Left unaided, the probe continued to descend and ultimately impact on the surface. There was, however, sufficient fuel in reserve for 3 trajectory alterations to increase altitude and give the probe a short time extension to continue its work into 2015. A third mission to Mercury is underway by the European Space Agency and the Japanese agency JAXA. Bepi Colombo is named after the Italian mathematician Giuseppe Bepi Colombo, who first developed the gravity assist maneuver for NASA with the Mariner 10 probe. It consists of 2 orbiters, the ESA Mercury Planetary Orbiter and the Japanese Mercury Magnetospheric Orbiter.
What scientists want to do is try to understand the nature of the planet itself. What material is on the surface. We would like to measure temperatures. We would like to see the interaction with the solar wind. Then Mercury has a magnetic field, which is like Earth, a dynamo field. We would like to understand that.
The Japanese MMO will focus on the magnetic field environment around the planet, while the ESA probe will focus on the planetary surface. Like the previous 2 probes, Bepi Colombo will use Earth and Venus to slow the probe's speed down to drop closer to Mercury's orbit. This trajectory will take approximately 7 years to accomplish. with solar electric motors to maintain deceleration, then a conventional rocket engine will be used for orbital insertion. The orbital life of the probes in the harsh environment is expected to last 1 to 2 years. The two craft carry a suite of the most advanced instruments, including a laser altimeter and magnetometer, infrared and ultraviolet spectrometers, imaging X-ray and high-resolution stereo cameras. Bepi Colombo is designed to answer specific questions about this planet. Why is the planet so dense? How did it form? Is the planet tectonically active? Why can no iron be identified on the surface? In the absence of any ionosphere, how does the magnetic field interact with the solar wind? How is the magnetic field generated?
We have a theory to understand how planetary systems form. Now, the theory was based on explaining the solar system, and it was fine, it worked. But now, when we have discovered new planets around other stars in the galaxy, the extrasolar planets, they don't fit at all. So something is wrong. And the special cases, those that are difficult to understand in the details, like Mercury, are very helpful.
By finding answers to some of these questions, Bepi Colombo will help us understand how the solar system was formed 4.5 billion years ago. It is the first and brightest star you see at night. Our sister planet in some ways, our closest planetary neighbor in both distance and diameter. However, Venus is difficult to reach and a very strange world when you get there.
In the early days of the solar system, Venus and Earth must have been very similar. But then something happened and they took a different route in its evolution.
Venus is the only planet in the solar system that needs more time to rotate once around its own axis than it rotates around the Sun. There must have been a major disaster in the early history of the planet where it collided with a big other object. And this made it stop its rotation. The problem is that without the protection and without the rotation, the planet lost its water and so it's completely dry. And this, in the end, led to a horrible greenhouse effect that caused the temperature to rise to the levels that we see
One of the main differences between Venus and the Earth is simply that Venus doesn't have a magnetic field. So the way it interacts with the star is completely different. If you want to understand how did Venus get that way, why does Venus not have any ocean, you need to understand the interaction between the star and the planet.
The Soviet Union and the United States sent probes with some success. 3 Mariner spacecraft made brief flybys, and the Soviet Veneras entered the atmosphere and touched down, some surviving for minutes. They managed to send back tantalizing images of an almost serene vista. NASA sent 2 more probes, Pioneer Venus 1 and 2, the latter depositing 5 small probes onto the surface. The Soviets continued their program of Venera probes with 4 successful landers and orbiters. A further 2 Russian Vega missions deposited atmospheric probes as they swung by en route to Halley's Comet.
The atmosphere of Venus is incredibly interesting because it's so different from the Earth's atmosphere. And we'd like to understand what causes these differences, because this might well help our understanding of climate change on planet Earth.
There's a very dense atmosphere, to 97% of carbon dioxide, a very strong greenhouse effect, and the temperature down on the surface is more than 450 degrees Celsius. and the surface pressure is 92 bars. It's almost 100 times more than the Earth. So it's a very, very unpleasant place to be.
High up in the clouds, about 100 kilometers from the surface, the wind speeds are very, very high. The wind is traveling at 300 kilometers an hour, and it travels around the Earth, around Venus every 4 to 5 days. So that's one of the things we don't understand, why at the surface the winds are very gentle, and high up the winds are very, very fast. So it's a very different atmosphere to the Earth's atmosphere.
0 and liftoff of Space Shuttle Atlantis.
In 1989, the NASA probe Magellan was launched from the payload bay of Atlantis en route to Venus, its 5-year mission to radar map the entire planet's surface. The radar managed to peer through the dense atmosphere and revealed the true face of Venus. What it showed was a young surface with few craters and mostly covered with volcanic activity, lava flows and large lava plains. Surprisingly, there was little evidence of wind erosion, and the surface plate tectonics were dominated by global rift zones, unlike Earth. To date, that was the last Venus probe from NASA. It was 12 more years before Venus came under scrutiny again, this time by ESA's Venus Express. To conserve fuel for a long mission, the probe utilized aerobraking in the Venusian atmosphere to make orbit.
Very interesting discoveries of Venus was a huge vortex, a huge cloud at one of the poles of Venus that in some ways looks very similar to a hurricane on the Earth. But this is a long-standing event that's there all the time. We don't understand how it's formed, why it's there, and how it will evolve.
When we arrived at Venus 8 years ago, we detected winds at 300 kilometers per hour, very fast. But what has happened during these years, until now, they have actually increased. We now see winds of 400 kilometers per hour. And we can't really explain why that has happened.
More questions were raised by the planet's absent magnetic field.
Venus doesn't have a magnetic field. So Venus is just this big rock with this atmosphere and the ionosphere sitting in space, and the supersonic solar wind with the interplanetary magnetic field whacks into Venus, and it can't penetrate through the ionosphere. So the interplanetary field lines just sort of pile up ahead of Venus, like cars on a freeway. This solar wind whacking into it essentially sort of strips off the atmosphere, and it literally forms this long tail, like a comet that's stretching out into space. Pioneer Venus Orbiter was the first spacecraft to really thoroughly explore that night side region where the atmosphere is all escaping away, and it discovered this really mysterious phenomena which has yet to be explained. Imagine that we're flying from pole to pole on the night side, so we're feeling the plasma around us, and then suddenly the ionosphere disappears, and then it sort of comes back. And this is what an ionospheric hole is. It's like a chasm in the sky, a big hole where the ionosphere is just absent. So Pioneer Venus Orbiter basically measured inside these things, and we saw that there is very little plasma, and there's all this magnetic field. And from that, they sort of suggested that this is essentially a magnetic structure that's sitting in the night side. I wanted to see if I could go looking for these things with Venus Express. What we saw is essentially this really exciting, strong, straight magnetic field lines that we expected, and really boring plasma signatures. It shows us that this is a magnetic structure, right? This is a tube of interplanetary magnetic field that, well, PVO saw it coming out of the ground, and now we've seen it way out in the tail. So these things really continue out to much higher altitudes than we previously have found them at.
As Venus Express neared the end of its mission, scientists made some risky aerobraking maneuvers to bring the probe much lower in orbit to make close-up observations of the planet. These maneuvers involved daring plunges into the hostile atmosphere only 130 kilometers above the planet's surface.
For the aerobraking, we wanted the most area possible to get the most friction possible, but that also generates heat. And so what we did was we went into the atmosphere in this direction, because this face of the spacecraft, which had been attached to the rocket originally when it was launched, was most able to take the forces and the temperatures. We also turned the solar panels so that the side with the actual solar arrays was in the back to maximize the area as we went through the atmosphere, to maximize the amount of friction and to get the most amount of braking. What we saw that was a little unusual is the variability in the pressure, as if there were waves within the atmosphere. And so that possible wave-like structure was not expected. And analyzing that data will keep scientists busy for a little while yet.
Venus Express carried a suite of 7 instruments: magnetometer, spectrometer, and several cameras to study the atmospheric winds and surrounding space environment. Venus Express outlived its planned 2-year mission by another 7, and only recently was it directed to ditch into the planet's atmosphere. The Japanese have made the most recent attempt to reach Venus with Akatsuki, whose planned observations are to include cloud and surface imaging with infrared cameras. Their main focus is the Venusian meteorology, including confirming the presence of lightning and any current volcanic activity. The probe failed to enter orbit on its first attempt, and JAXA are hopeful when the probe's heliocentric orbit returns it to Venus that a second attempt will succeed very soon. There are many plans afoot to return to Venus. Even a manned mission has been studied by various groups. One such study conducted for NASA produced HAVOC, a high-altitude Venus operational concept. It would rely upon 2 spacecraft sent into Venus orbit, the first unmanned atmospheric descent stage and the second orbital return craft carrying the crew. They would dock, transfer crew to the descent stage, and proceed to deorbit. Once into the upper atmosphere, a parachute would deploy, slowing the descent and allowing the deployment of a dirigible craft to inflate and carry the crew at high altitude. From there, they would study the planet below. The return journey for the crew would begin with a high-altitude launch back into orbit, where they would dock with the orbiter, transfer crew and equipment, and then make the journey back to Earth. There they could dock with an Orion capsule for the return to Earth. Mars, the god of war and the source of man's science-fictional demise. It has fired our imagination for thousands of years. We know the dry, barren planet was once flowing with vast reservoirs of water, the sky thick and filled with clouds, and the tantalizing possibility of life. It is the only other place in our solar system that man might one day call home. We Earthlings have fired numerous probes and satellites towards the Red Planet, an invasion of sorts, not for conquest, but for knowledge. What happened to Mars? Is there or has there ever been life on the planet?
A fundamental question that needs to be answered is life as we know it on Earth, even the simplest type of microbial life, unique? If we were to go to Mars and we were to find evidence of early microbial life, or maybe even present life that somehow survived in the near surface, would it be the same as the early life that developed on Earth? That's a very fundamental question. Does life emerge generally in planets where the conditions for life are favorable, if we find out that they were favorable on Mars? Or might life take its own unique path in different environments and turn out differently?
We have bombarded Mars with satellites and landers, but there have been more failures than successes. The Soviets established 2 Mars orbiters, while NASA landed 2 Viking landers carrying complex analytical laboratories and searched for signs of microbial life. Their findings were inconclusive. Further missions to Mars still had a high mortality rate, but the successes were outstanding, with robotic probes operating for years beyond their initial missions. In fact, Mars is a planet occupied solely by robots on the surface and satellites peering down from above. All these instruments perform admirably in their specified fields of endeavor, giving us a much clearer picture of the planet and its history. The science was following the water, what happened to it, and where it is now.
Thanks to the specific instrumentation on board the mission, we are able to tell us what kind of ice did we find. And the result is that there is a mix of CO2 ice, or carbon dioxide ice, and water ice. And it's very important to characterize it, especially for the water ice or frozen water, because one of the main objectives of any mission to Mars is to trace the water on Mars in every form, liquid if possible, solid, water vapor. So it's very important to study the ice because it's one of the reservoirs of water on the planet.
The science was conclusive. There was water on Mars. There were ancient lakes and rivers, even an ocean. We needed to learn more. With the advancement of analytical technology, computer power and robotics, a new rover was constructed. Big, complex and heavy, it required a new way to land on Mars safely. Engineers came up with a system that couldn't be fully tested here on Earth. It required a lot of things to happen correctly, on time and in order. This was the Sky Crane, and the rover Curiosity was the first to try it out. A controlled re-entry with heat shield, aerobraking with a parachute, all pretty standard. Then a rocket-powered Sky Crane drops from the aeroshell and gently descends toward the surface, spooling out the rover below on cables. The rover touches down, cuts the cables, and releases the Sky Crane to fly off and crash harmlessly. The Curiosity rover has been an astounding success, traversing the terrain for over 10 years, taking samples, drilling and studying rock formations, zapping samples with a powerful laser, and photographing its progress.
Now, in the belly of that rover is an instrument called SAM. It's an instrument suite that has a couple different instruments in it that allow us to look at different types of gases. It helps us understand the chemical composition of the atmosphere and the end of minerals that might be found in the rocks and the soils on the surface. In particular, it helps us identify organic molecules that might be present.
So the sorts of evidence we're looking for, sorts of signatures of past life that we would be looking for would be signatures of microbial life. So not realistically looking for dinosaur bones and that kind of thing. If life ever existed on Mars, we expect it to have been microbial, microorganisms.
Orbiters, including Mars Odyssey and Mars Express, have been hunting down life as well from orbit.
After 10 years of mission, we have achieved a global view of Mars, and then we know at every location on the surface if you find some special minerals or not. So we have really the global view that tells us the history of Mars. Mars Express has, for the first time, detected methane, and also the concentration in the atmosphere vary from a place to another, from a season to another. And this discovery has been very debated in the scientific community because, in fact, methane should not be there because it's being destroyed in the atmosphere by the ultraviolet radiation. So if methane is there, there must be a source of methane, and for the time being, the origin of this source is largely unknown.
However, with Curiosity prowling around Gale Crater, it too detected seasonal methane.
Now, methane has been found previously in the Martian atmosphere by both Earth-based telescopes and spaceborne orbiters. But this is the first time that we've actually seen a sharp increase and decrease in the abundance of methane in the atmosphere in Gale Crater. What this really means is that present-day Mars is an active environment.
The big question is, what is the origin of this methane now being released? The two principal areas are, first, by analogy with the Earth, it could be released and produced initially primarily by biology. This would be microbial activity acting on certain chemicals below the surface and then producing methane as a byproduct. But of course, we can't state with certitude that it is biologically produced. And so we also consider geochemical mechanisms in which carbon dioxide is actually combining with water and producing methane under very high temperatures and pressures. And that methane can then be released in the atmosphere separately.
Now, at this point, we don't have enough evidence to tell us whether or not the organics we're finding are biological or non-biological in origin. There are several viable non-biological explanations, including this organic material could have come down from space, from meteorites or comets, or organics can be formed by geological reactions in the rock itself. Now, what's exciting about this discovery is it gives us new hope in the search for chemical evidence of life. We found the organic material. Now, the next step is trying to figure out what its origin is.
Main engine start, ignition, and liftoff of the Atlas V with Maven, looking for clues about the evolution of Mars through its atmosphere.
The latest NASA orbiter mission is Maven. Launched in November 2013, it made orbit 10 months later.
Maven is the Mars Atmosphere and Volatile Evolution mission. Our goal is to study the role that loss to space has played in the history of the atmosphere. Where did the water go? Where did the CO2 go from the early planet? These are important questions to understand how Mars went from an early warm, wet environment to the cold, dry environment we see today.
There's evidence of water flowing on Mars at one point in time, perhaps even oceans on Mars. And what happened that it's so barren at this point in time? And a key part of that is the atmosphere, and it's a much thinner atmosphere than what scientists believe it was at one point in time. So the stripping away of that upper atmosphere, that's what Maven is going after, the climate change at Mars.
One of these processes is called sputtering, where atoms are knocked away from the atmosphere due to impacts from energetic particles. The sun constantly emits high-energy photons. When these enter a planet's atmosphere, it can crash into a molecule, knocking loose an electron and turning it into an ion. When this happens in the presence of a magnetic field, the ions are captured and spin around the field. Conveniently, the sun generates a giant magnetic field that is carried by the solar wind. As the magnetic field sweeps past the planet, these ions are carried away. Depending on where they form, other ions will not be carried away but will hit the top of the atmosphere. These ions crash into other molecules and fling atoms everywhere. Some of these atoms can be knocked or sputtered into space, causing atmospheric loss. As this process continues over billions of years, Mars' atmosphere has disappeared, and along with it, the water. How much water has Mars lost this way?
We used the world's 3 major telescopes for infrared astronomy. From the ground, we could actually take a snapshot of the whole hemisphere of the planet on a single night.
Water naturally carries a heavy isotope of hydrogen, deuterium, which remains trapped in the water cycle while normal hydrogen is lost to space. Detecting the amount of deuterium enrichment tells us how much water has been lost.
Now we know that Mars water is much more enriched than terrestrial ocean water in the heavy form of water, the deuterated form. Immediately, that permits us to estimate the amount of water Mars has lost since it was young.
So in the ancient past, we have some indications of water was flowing on the surface, but how much water was there? We're talking about oceans, are we talking about small rivers, little rain? So these definitions of how much water was on the planet was very undefined.
A major question has been how much water did Mars actually have when it was young, and how did it lose that water?
The findings indicate that only 13% of an ancient ocean remains on the planet today, now stored in the polar ice caps. 87% of this ocean has been lost to space. This means that early Mars would have looked much different than it does today, with a significant portion of its surface covered by water.
So the really interesting question is, could it form a sea or an ocean? And indeed, it would. In the northern plains, which is a relatively flat region but depressed from the rest of the planet, it would form an ocean that was approximately 20% of the planet's surface area. And so that is a respectable ocean.
This ocean had a maximum depth of around 5,000 feet or around 1 mile deep. It's deep, not as deep as the deepest points of our oceans, but comparable to the average depth of the Mediterranean Sea.
By combining Martian topography with the new estimate for water loss, the researchers were able to simulate Mars's ancient ocean and its escape to space. As Mars lost its atmosphere over billions of years, it lost the pressure and heat needed to keep water liquid, causing the ocean to shrink and recede northward. The remaining water eventually condensed and froze over the north and south poles, giving Mars the ice caps that we see today.
We now know that Mars was wet for a much longer time than we thought before. Curiosity shows it was wet for 1.5 billion years, already much longer than the period of time needed for life to develop on Earth. And now we see that Mars must have been wet for a period even longer.
It's fascinating that we can learn so much about 4.5 billion years ago what measurements are taken right now. And ultimately we can conclude this idea of an ocean covering 20% of the planet, which opens the idea of habitability and the evolution of life on the planet.
Building on this knowledge, scientists are developing the next series of robotic probes to be sent to Mars in the coming years. This time, NASA is building on its successes, utilizing hardware and systems that they know will work.
We've been to Mars before with the JPL Lockheed Martin team. We've been to the surface of Mars before successfully with Phoenix. We know how to operate the arm. The surface operations are much, much simpler than Phoenix. We're putting 2 instruments on the surface and then we're leaving them there with no ground-in-the-loop interaction, repetitive, weekly uplink downlink sessions. We're just made to do this mission.
The InSight mission is a geophysical mission to Mars. It's going to go to Mars and take its vital signs. It's going to take its heartbeat, the seismic activity of the planet.
So we're going to be doing that using a seismometer, a very high precision seismometer, using techniques that have been well developed on Earth to get the understanding of the crust, mantle, and core and sort of the relationship between those.
Going to take its temperature by measuring the thermal gradient of the surface, which tells how much heat is coming out.
We also have a heat flow probe, we call it HP cubed, and what that does is it's going to basically take the temperature of Mars, and from that it'll be able to understand what the thermal flux is over the course of a full Martian year.
And it's going to sort of measure its reflexes by looking at how the rotation wobbles with the tidal effects of the sun.
Our final experiment is called RISE, and that's going to be looking at the basically the wobble of Mars to help understand what the core size may be in composition.
The European Space Agency is also well along with ExoMars, a rover with advanced drilling capability due to be launched by 2018. Its principal goal? To drill down deep in search of microorganisms.
What is new with ExoMars, with the rover in particular, is what we call the mobility. Mobility not only horizontal, but also vertical. And this is a peculiar thing that we have on board the ExoMars mission. So we will be able to sample material from below the surface. That is quite important to understand if there is any sign of past life activity on Mars.
We will be looking for the first time in the third dimension being depth. And we think that is where we have the highest chance of making an interesting discovery regarding the presence of organic molecules in Mars.
It's a whole planet out there with a complicated history. That history is a story that's stored in the rocks, and our job is to figure out that story and what that story of that planet tells us about this planet that we live on.
So where Curiosity takes rocks and grinds them up into powder and looks at their bulk constituents, what this mission would need to do is be able to look in a microscopic level and examine the rocks for these very tiny and detailed messages that they would be sending to us about the past life that could have lived there.
This that I'm holding up here is a classic biosignature from the Earth. It's a fossil. We're not actually expecting to see a fossil of shells or other components, but what we want to be able to see are, with this instrumentation, are the fine scale layering that one might see in a rock, in which we can see dark and light toned layers. And those dark and light toned layers are telling a story.
When will NASA send astronauts to Mars?
4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
The first test flight of the Orion crew capsule is complete. The hardware and systems are ready for mass production. The components, the engineering, the manufacturing are all underway, with NASA looking back to what worked in the past and utilizing it for the future. The solid rocket booster technology straight from the space shuttle has been extended and tested. NASA's new Space Launch System, or SLS, is coming closer to fruition, reusing the space shuttle's main engines as the new system's workhorses, saving billions of dollars and years in research and development. The Europeans are teaming up with NASA to provide the service model for Orion, allowing for long-duration, deep space flights. autonomous Martian landing systems are well advanced and being tested. Software and hardware are fully integrated for both manned and unmanned Martian landings. And when they get there,
Desert RAT stands for Desert Research and Technology Studies. This is a group of engineers and scientists.
We're looking to test out new concepts, procedures, equipment, like rover concepts, to see how they work in the field environment.
So the team tests these technologies to make sure that in future human spaceflight missions we'll be able to do science as best as we can. That's something that NASA's never done, 2 human rovers at the same time. So we're really trying to develop how do you use these assets at the same time, and interesting things that you might not think about are your communications. So you potentially have 4 astronauts talking all at the same time to mission control or science communication background.
It's just like running a real mission, say, like you can think about the Apollo mission to the moon. You had the astronauts to the moon and you had the people mission control, but there was a science backroom you didn't hear about, but the astronauts were getting information from them.
Arizona has a very good climate for these types of analog studies. You have pretty much open plains and you have a lot of geological features that are analogous to places on the moon and on Mars.
long-term space voyages are being replicated on the ground and in orbit with the ISS. Surface habitats, power systems, food and oxygen supply manufacturing are also on the drawing board.
The human flight component would like to see an experiment where resources on the surface of Mars, from the rocks or the atmosphere, could be used to generate fuel or other parts that would enable future exploration in cutting the tie, so to speak, to Earth. So you wouldn't necessarily have to bring everything with you. You can actually manufacture it on the planet. And that's a really exciting additional component that we've been exploring and analyzing in this work.
NASA isn't the only one with its eye on this prize. ESA and now the Indian Space Research Organization have a spacecraft orbiting Mars, and they did it on their first attempt. Private enterprise is hard at work as well. Mars 500, Mars One, the Mars Society, Mars Foundation, and the Mars Initiative, to name a few. And they have volunteers lining up already for a one-way trip to Mars. It is inevitable that we will set foot on Mars in the very near future. We will stay and learn her secrets. Perhaps in the future we will be able to alter the atmospheric density through terraforming and return Mars to the world that it once was, awash with oceans and rivers, clouds and rain. Maybe some of us could call it home. In the cold, dark expanse of our solar system, beyond the asteroid belt, lie the giant planets. Some can be seen with the naked eye, others only glimpsed once by a passing probe. We are again sending cameras to the edge of the solar system to bring us new insights into the evolution of our worlds. Pioneer 10 and 11 made the first passage through the asteroid belt, leading the way for the venerable Voyager missions. These two probes made a grand tour of the outer solar system before slipping away into interstellar space. Jupiter, the first and greatest of the outer planets with its broiling sky, has had fleeting visits from other missions like Ulysses, Galileo and Cassini, each adding to the mosaic of Jupiter and its violent atmosphere.
My name is Amy Simon Miller, and I study the atmospheres of the Jovian planets. Weather on Jupiter is confined to a rather thin layer, kind of high up in the atmosphere. So the tops of the clouds are what we're seeing when we look at Jupiter. One thing we're seeing in the southern part of the equatorial region is little V-shaped clouds or chevrons, and we wanted to understand how those are moving in the atmosphere.
What we think chevrons are simply holes in the clouds. They're simply areas where we don't see any bright white clouds.
The Cassini mission flew by Jupiter in the year 2000, and because it was a slow, distant flyby, we got a lot of coverage of the planet over a long time period. So we were able to put those images together and make movies.
Using these movies, we observed Rossby waves that caused north-south meanders in a jet stream south of the equator. With new movies, we instead focused on hotspots. Hotspots are unique because we believe that there is a Rossby wave similar to what we previously detected, but instead of this Rossby wave moving north-south, it primarily moves up and down in the atmosphere. The downward portion of the wave pushes air down into warmer layers of the atmosphere. This causes any clouds that are embedded within the wave to evaporate and prevents further clouds from forming. So at any given time, there are approximately 8 to 10 hotspots in Jupiter's atmosphere that are spaced roughly evenly apart from one another. We believe that each of the downward portions of this Rossby wave corresponds to the hotspots that we see on Jupiter. This new finding is exciting because it'll allow us to re-examine the Galileo probe data and allow us to better understand it and better place it in the context of Jupiter's overall global climate and atmosphere.
The latest probe to be specifically aimed for Jupiter is Juno. Launched 2011, the probe will reach Jupiter after a 5-year journey. Juno's goal is to investigate Jupiter's interior structure and magnetosphere and help improve our understanding of the formation of the planet and therefore the history of our solar system.
Juno spins like a propeller, where the propeller's kind of facing the sun because they're all solar powered.
If you spin something, it stays spinning. It's like a gyroscope. We can use a spinning spacecraft to let each instrument get its turn to see Jupiter. We get to go very close to the planet, inside the radiation belts instead of outside the radiation belt. We're in a polar orbit, so by small adjustments of the timing, we can map the entire planet. We can get repeated stripes at different longitudes as Jupiter spins underneath us.
It does mean that Juno is going to see the polar regions to a greater extent than with other spacecraft, but I think the most important thing is that it gets in very close to the planet as part of that ellipse, brings it in a few thousand miles above those cloud tops, very close, near the equator.
We're going to go over the poles of Jupiter. That means we can study the magnetosphere in a different way.
A magnetosphere is the sphere of influence of a magnetic field. So a planet that has a magnetic field has a magnetosphere when its sphere of influence extends beyond the planet out into space and affects the region around it. The magnetosphere of Jupiter is vast. So if you think of Jupiter being 10 times the size of the Earth, and the magnetosphere is 100 times the size of Jupiter.
The Juno probe is the furthest NASA has sent a solar-powered spacecraft. Sunlight provides 25 times less energy than on Earth, which means it requires advanced solar power technology with solar cells which are both 50% more efficient and more radiation tolerant than silicon cells. The craft also houses an electronics vault, which is radiation shielded to protect the electronics aboard from the intense and deadly radiation environment around Jupiter. The probe carries a full set of sensors: a microwave radiometer for atmospheric sounding and composition study, plasma and energetic particle detectors, a vector magnetometer, a radioplasma wave experiment and ultraviolet, and an infrared imager, plus a color camera called JunoCam.
In Roman mythology, which of course is rooted from Greek mythology, Juno was the wife and sister goddess of Jupiter. And Jupiter was sort of being naughty with some friends, so he cast a veil of clouds around himself and his friends. But of course, Juno was a fairly powerful god herself and used her powers to look right through the clouds and see the true nature of Jupiter and understand what he was really up to. And that's exactly what the Juno spacecraft does for us, is that it goes there with special instruments in a special orbit and uses its powers to see right through Jupiter's clouds and understand its true nature, which is holding these secrets for us about how the solar system formed and where we all came from.
A long-standing feature of the storms of Jupiter is the Great Red Spot. Large enough to swallow the Earth, this storm system has been studied since the 19th century. Then it was measured at a little over 41,000 kilometers on its long axis. Voyager 1 and 2 measured it at over 23,000 kilometers, and recent observations by the Hubble Space Telescope have the red spot at only 16,500 kilometers long. It seems the rate of shrinkage is increasing. One day it will probably vanish altogether. Juno will also help confirm the theory that Jupiter was the first of the planets in the solar system to form from the primordial disk of dust and gas some 4.6 billion years ago.
I would expect Juno to tell us more about how planets work, meaning how the heat gets out, what kinds of flows exist inside the body, how magnetic fields get generated. Learning what Jupiter is made of, we will learn such a wide range of things. For indeed, Jupiter is the most massive planet in the solar system. It is the body you want to understand in order to understand the architecture of everything else, including Earth.
Juno's year-long mission will end with a deorbit burn and a slow descent into the upper atmosphere, where it will continue to send back scientific data until its destruction. Perhaps the jewel of the solar system is Saturn, with her spectacular rings. All four of the outer planets have rings of ice and rock, but Saturn's is the most complicated, and with thousands of ringlets, the most visible. There are several groups of rings classified A through to G. Some are formed by shepherd moons within the rings, and by gravitational tidal effects from others outside. Yet some gaps are still unexplained. The current spacecraft at Saturn is Cassini on its second extended mission, the Cassini Solstice mission. which is expected to be completed in 2017. It continues to watch the planet-sized storms in the atmosphere.
Great white spots on Saturn are these large storms that erupt about once every year on Saturn. A year on Saturn is 29 Earth years. The great white spot that erupted in December 2010 initially presented itself as a small little white fluffy cloud that came up, and various instruments on Cassini were seeing it, and ground-based instruments seeing it as well. And as the days progressed, the storm got larger, and then it got sheared from the top and the bottom of the storm on either side of it, and it wrapped all the way across the planet. We'd never before been able to study a storm system of this magnitude in the infrared, so we are very fortunate at this time to have a spacecraft in orbit and excellent ground-based facilities, allowing us to make a historical record of this great white spot. And that will allow us to compare it in future generations when the next one happens.
Another phenomenon is a hexagon of clouds around the North Pole of Saturn, which has recently come into the light.
Cassini has been in orbit around Saturn for 9 years, and we've been following this hexagon which surrounds the North Pole. It's bigger than 2 Earths, and it's a wandering jet stream. But it's been winter in the north, so we have not been able to see what's at the center of the hexagon. But now it's spring, and what we found at the center of the hexagon is a Saturn hurricane. This is a view from directly over the North Pole, which is made possible by the orbit of the spacecraft, which is now taking us over the poles. The winds are flowing at 300 miles an hour, which is 4 times hurricane force. The fluffy white clouds in the center are about the size of Texas. We can use special filters to measure the heights of the clouds, and red are low clouds and the green are high clouds. We call it a Saturn hurricane because it has the eye, it has the high winds, but it's different from an Earth hurricane because it's locked to the North Pole. And unlike a terrestrial hurricane, there's no ocean underneath. And that's one of the puzzles we're trying to figure out.
A phenomenon first observed on Saturn by Pioneer 11 in 1979, and common to Earth as well, are polar auroras. These magnetic-generated light shows are far more spectacular on Saturn, rising hundreds of miles above the planet's poles. And unlike on Earth, where bright displays fizzle after only a few hours, auroras on Saturn can shine for days. Auroras are produced when speeding particles, accelerated by the sun's energy, collide with gases in a planet's atmosphere. The gases fluoresce, emitting flashes of light at different wavelengths. The Hubble Space Telescope has been watching them closely.
Starting in 2016, ending in 2017, these orbits will take us up and over the north and south poles of the planet.
We're actually going to dive in between the innermost edge of the D-ring and the upper atmosphere of the planet itself.
From that, we're going to learn how is Saturn constructed from inside out.
We'll also get the magnetic field of the planet, the mass of the rings for the very first time, and get to sample a place that no spacecraft has ever flown before.
This is a mission that cannot be duplicated. So we really want to take advantage of this opportunity to observe seasonal variation in the system.
Uranus has had only one visitor from Earth, Voyager 2. Like the other gas giants, Uranus has a ring system, a magnetosphere, and numerous moons. There the similarities end. Images from Voyager revealed a featureless atmosphere with no cloud patterns or storms. Uranus differs in its orientation as well. Tilted onto its side, its poles lie where other planets have their equators. Its magnetosphere is off-center and tilted as well, generating an unusual asymmetrical field. This causes Uranus's auroras to be well off the poles. Observations from Earth have shown seasonal change and increased weather activity as Uranus approached its equinox in 2007. The wind speeds on Uranus can reach 250 meters a second. Although there are currently no scheduled missions to Uranus, there have been several proposals put forward, both jointly from ESA and NASA and JPL, including both nuclear and solar-powered probes and an atmospheric descent probe. Ion propulsion is favoured because it allows a greater mass to be sent to the planet. Ideally, a probe could be launched in 2020 with a 13-year cruise to Uranus. As this is considered a low-priority mission, no funding has yet been allocated. The eighth and last planet in our solar system is Neptune, the last of the gas giants. Made of hydrogen and helium, it has trace amounts of methane, which gives the planet its beautiful blue color. It too has only been visited once by Voyager. The detailed images taken at that time revealed white clouds and a massive storm marring its atmosphere with supersonic winds.
The storm revolves around the planet every 18 hours. And then it rotates around its own axis like a big glob of pizza dough every 16 days.
Voyager also identified a ring system and confirmed 14 moons. Triton is its largest and is believed to have been captured by the planet from the outer Kuiper belt. Voyager also discovered Neptune's magnetic field was off-center and tilted, not unlike Uranus. Both Uranus and Neptune have had very little close-up study, and various missions have been proposed to fill the gap in our understanding of these ice giants. NASA has looked into several possible missions back to Neptune, perhaps a similar probe design to that of Cassini-Huygens, but due to fiscal and other constraints, none have been approved.
The Voyager mission to the outer planets has certainly been a journey of a lifetime. Having encountered Triton as the last world we would visit, I don't see how any of the scientists could have been happier.
Next stop was Pluto. When New Horizons was conceived, built and launched, Pluto was still a planet. The downgrade to dwarf made little difference to its investigation.
Well, you know, the key to planetary science is that you really have to go places to get the resolution, to get up close enough to really see what's going on. We want to get up close and personal.
New Horizons is the first really of a whole new breed of spacecraft that is focusing on a very specific task.
For this mission, the questions are basic. What do Pluto and Charon look like, and what are they made of?
We had to really be disciplined and say, we can't do everything. Let's focus on the primary questions and design the instruments to answer those primary questions.
New Horizons was built light and launched on a very powerful rocket, breaking all previous speed records when it left Earth on a solar escape trajectory at 16.26 kilometers per second. The spacecraft passed the orbit of the Moon in just 9 hours. It then cruised for just 1 year to reach Jupiter, where it was given a gravity boost, increasing its speed by 2 kilometers per second and cutting the travel time to Pluto by 3 years. New Horizons was the first to visit the dwarf planet and Charon, its largest moon. Pluto failed one of the 3 criteria to remain a fully fledged planet. It has not cleared the neighborhood around its orbit. Pluto is part of the Kuiper Belt and not the only dwarf planet residing there. This is an image of Pluto at its closest approach. It still remains a treasure trove of scientific questions and hopefully answers about the origins and evolution of the solar system. From Pluto's flyby, it is on to the unknowns of the Kuiper Belt. The most numerous objects in the solar system are the ice dwarf planets that make up this donut-shaped region on the edge of the solar system.
It's kind of like the asteroid belt, but much bigger. It has hundreds of times more objects in it than the asteroid belt.
The spacecraft will visit some of these objects in its travels.
Once you have the orbit, and we know where the spacecraft is and where it's going to be, we can figure out how much fuel the spacecraft is going to need to use to get to these objects.
After some careful calculations,
it looked like we might actually have to burn the engines to miss the object, which was a pretty exciting concept. You know, it's a good thing we looked, because you wouldn't want to run into one of these things.
These cold classicals, they're pretty much as they were 4.5 billion years ago. They're little fossils. That's incredible. We have no idea what they're going to look like.
New Horizons will continue to explore the outer solar system until 2026. There are many worlds within our solar system. Most reside beyond the asteroid belt. These are the moons of the gas giants of the solar system, each a unique and mysterious world of its own. Some have oceans of water, geysers of sulfur, or atmospheres of plastic. Some are just now being seen at the outer rim of our solar system. All are worthy of much more scrutiny. Currently en route to the Jupiter system is the scientific probe Juno. It will be the first orbiter mission to Jupiter since the troubled Galileo spacecraft in 2003. Its task? To establish a highly elliptical polar orbit and study Jupiter in the greatest detail so far. Several other probes have made flybys of the system en route to other destinations. Some of these returned fascinating data on the Jovian moons. Jupiter, the largest planet in our solar system, has, as far as can be ascertained, 67 orbiting satellites. Most of them are odd-shaped rocky masses, probably asteroids like Amalthea, trapped in the massive gravitational field of the planet. However, there are 4 major satellites of Jupiter, each large and dense enough to form spherical bodies. These are called the Galilean moons, named after the great Italian scientist and astronomer Galileo Galilei, who discovered them in 1610. Io is the smallest of the Jovian moons, though somewhat larger than our own moon and closest to orbit Jupiter. The intense gravitational effects causes the violent and active nature of the moon. It has over 400 volcanoes, lava flows, and plumes of sulfur 300 kilometers above the surface. The most dense of the four moons, Io is also the driest. Io is thought to be composed of mainly silicate rock with a molten core of iron or iron sulfide. Most of the surface is composed of extensive plains coated with sulfur and sulfur dioxide frost. The surface is geologically young, which accounts for the lack of impact cratering. Unlike all the other planetary bodies, these craters have been covered over by volcanic activities. Numerous active volcanoes also eject material high above the moon and into orbit around Jupiter. The internal energy for this overactive moon is due to gravitational tidal forces between Jupiter and the other moons orbiting further out from Io. Just slightly smaller than our own moon, Europa has an icy crust covering what is believed to be a salty global ocean capable of sustaining indigenous life. It also has active geysers ejecting material into space.
So how do we think we know that Europa's ocean exists? Well, it's a combination of using telescopes on the ground and having spacecraft that have flown by Europa and collected data about the surface, about the interior structure, and about the magnetic field around Europa. And the combination of those data sets leads us to a high degree of confidence that this global liquid water H2O ocean is there today, and it's been there for much of the history of the solar system. And here's where Europa is a real game changer. It is far, far out from the sun, and yet it's got this liquid water ocean. And the reason that Europa has liquid water is because it's orbiting Jupiter, and the tidal tug and pull causes Europa to flex up and down, and all of that tidal energy turns into mechanical energy, which turns into friction and heat that helps maintain this liquid water ocean beneath an icy shell. Along with helping maintain liquid water, we think that tidal energy may also allow that ocean to interact with rocks on Europa's seafloor. And it may even give rise to things like hydrothermal vents, which could help provide not just the building blocks for life, but also the energy for life.
Europa is the most likely place to find life in our solar system today, because we think there's a liquid water ocean beneath its surface. Now we know that on Earth, everywhere that there's water, we find life. So could Europa have the ingredients to support life?
We might be actually looking at a body that is presently alive, presently active, and presently undergoing its geology. There is too much evidence right now lying around on the surface, the red stuff, that suggests that something's going on there. Is that an environment that is habitable for any sort of life form? By golly, we really have got to go back and figure that out.
We have designed the Europa mission to take a spacecraft and its set of instruments all the way from planet Earth to Jupiter.
Previous mission concepts were for a spacecraft that would orbit Europa. But Europa is bathed in radiation from Jupiter. Any mission that goes in the vicinity of Europa is cooked pretty quickly. Instead, we're looking at a mission that will orbit Jupiter, make close flybys of Europa, and then zip out of the high radiation region. This allows us to have a mission that's many years long and to collect and transmit lots and lots of data. As Europa orbits Jupiter, it flexes And we could measure the gravitational change of Europa by encountering Europa at different points in its orbit. On a typical flyby, we would turn on our remote sensing instruments, we would image the surface, we would interrogate the surface with spectroscopy, and we would do the same thing on the way out. And we would essentially rinse and repeat, and do this many, many times until we understand Europa globally.
Images from the Hubble Space Telescope tell us that Europa might be emitting plumes of water high into space. If so, a spacecraft could fly through those plumes and sample it directly to understand the composition of Europa's interior.
If it does have the ability to harbor life, how does that work exactly? We'll have enough instrumentation to really pinpoint exactly how the mechanisms would work for replenishing the nutrients in a subsurface ocean.
Europa is so important because we want to understand, are we alone in the cosmos? If there's life in Europa, it almost certainly was completely independent from the origin of life on Earth.
And for the first time in the history of humanity, we have the tools and technology and capability to potentially answer this question. And we know where to go to find it. Jupiter's ocean world, Europa.
The Europa Clipper mission has passed preliminary development and strategy proposals and acquired further funding. The European Space Agency has been invited to develop an additional probe to ride along with the Clipper, as with the Cassini-Huygens mission, and either land or impact on the Moon's surface. The nominal Europa Clipper mission would perform 45 flybys of Europa at altitudes varying from 2,700 to 25 kilometers. A proposed launch window would be in 2025. If launched with NASA's new SLS heavy-lift rocket system, the probe would take less than 2 years to reach Jupiter. Otherwise, it will be a 6.5-year flight. The largest moon in the solar system, and another icy world, is Ganymede. Composed of silicate rock and water ice, the surface is heavily pockmarked by impact craters and regions of tectonic movement. The moon has a thin atmosphere of oxygen and possibly ozone and atomic hydrogen. The moon has a liquid iron-rich outer core and an internal ocean with possibly more water than Earth's oceans. Most recent modeling suggests the interior may be layers of water and ice, like a club sandwich. Ganymede is also the only moon known to have a magnetic field. However, it is embedded within the powerful Jupiter magnetic field and overwhelmed. But there are indications of auroral activity on the moon. Ganymede is also the final target for the Jupiter Icy Moon Explorer, or JUICE, the ESA-designated mission to 3 of the Jovian moons. It will be launched in 2022 from Europe's spaceport in Kourou, French Guiana, on an Ariane 5, arriving at Jupiter in 2030 to spend at least 3 years making detailed observations. It will visit Callisto, the most heavily cratered object in the solar system, and will twice fly by Europa. Callisto is the 4th and most distant of the Jovian moons from Jupiter, and outside the main radiation belt of that planet. Unlike its sister moons, Callisto has a very thin atmosphere of carbon dioxide and molecular oxygen, and low radiation exposure. Callisto is composed of silicate rock and water ice, and may also harbor a subsurface ocean. It is considered the most environmentally acceptable location for a manned base in the future. Saturn has 62 confirmed orbital satellites, many less than 50 kilometers in diameter. The bulk of the larger spherical moons are predominantly water ice and a small amount of rock. They include Mimas, Enceladus, Thetis, Dione, and Rhea. Enceladus is covered in ice with a subsurface ocean at the southern pole. Geologically active in the southern region, geysers have been observed. This would be from tidal heating and orbital resonance with Dione and Rhea, and could contain a liquid ocean heated by internal radioactive decay. However, the prize of the Saturnian system is undoubtedly Titan. Titan is the only moon with a dense atmosphere, and, other than Earth, the only body to have stable bodies of surface liquid. It is larger than both the planet Mercury and our own moon. Cassini deposited the probe Huygens on its surface in 2005.
Titan is Saturn's largest moon. It's actually the second largest moon in the solar system, and it's the only moon in the solar system that has a large and substantial atmosphere. And that atmosphere in some respects is really similar to that of the Earth, being composed mainly of nitrogen, but in other respects it's really different. It has methane as its second most abundant gas, and that takes the same role as water vapor in the Earth's atmosphere. It evaporates from the surface, it forms clouds, and then rains down again, and in fact forms lakes that we see at Titan's North Pole, including ethane and propane and all sorts of complex chemicals. We also see these vast dune fields at the equator, which are not made of silicates as they are on the Earth, but actually made of organic substances, essentially plastics, which have actually sedimented from the atmosphere and are being blown around into dune fields, the same as we'd see on a desert on the Earth. And through this we can detect which molecules are in the atmosphere. We see all the molecules that were previously discovered by Voyager. But we're also able to look for new molecules, and in fact, buried within the signatures of these more abundant molecular species, we saw a very small spike, which was due to a new species which had not been seen before. In fact, this was propylene. So the discovery of propylene on Titan is really exciting. First of all, it completes this chemical family where we had this missing link dating 32 years back to Voyager. But also it shows that there's much more there still in Titan's atmosphere to be discovered. Some people think that Titan is similar to the prebiotic Earth long ago, when the molecules were forming the basis of life. And we don't know what we're going to find on Titan if we send back further spacecraft with new instruments, more sensitive instruments, if some of the molecules on Titan could be similar to the basis of life on Earth.
NASA is preparing a new probe to follow in Cassini's footsteps. It is called the Titan-Saturn System Mission.
Cassini was able to look at the lakes, get a sense of the coarse composition of the lakes, but nothing about the organic molecules that are dissolved in the lakes. The Titan-Saturn System Mission is a 3-in-1 mission with an orbiter for Titan, a balloon that will float through Titan's atmosphere, and a lander that will splash down on one of the northern lakes of Titan. This mission will actually go into a lake, sample the liquid directly, see what the organic molecules are that are present. The Titan-Saturn System Mission also will go to Enceladus, the tinier moon, 1,000 times smaller than Titan, which has volcanoes, geysers essentially, that are spewing material from the inside of this moon outward. And it's a chance to see whether there might be molecules that would indicate that life has actually formed within the source region of these geysers. These geysers have water ice, and we strongly suspect that there's liquid water in the region that these geysers are coming from. We know there are organic molecules there because they've been measured by Cassini. The ability to follow this up quickly is essential because with Cassini-Huygens, we have now trained a generation of scientists who are ready to take a new generation of instruments and capabilities back to Titan and Enceladus and really answer the questions that Cassini-Huygens has left for us. And that continuity of knowledge and of enthusiasm is essential and very difficult to maintain in the outer solar system because trip times are so long. The Titan-Saturn System Mission really is Jules Verne realized. It's a kind of planetary exploration that we have never ever done before anywhere else in the solar system and can only be done on Titan. This mission will touch the human heart in terms of the way it's exploring this fascinating world. It will be floating on the surface of a lake. It will be floating through the atmosphere. It will be revealing the entire surface from orbit at the same time. As we think of exploration, of unveiling a new world, it's exploration in the true sense of the word.
The planet Uranus has 27 known moons, grouped in 3 categories: 13 inner moons, 5 major moons, and 9 irregulars. Only Voyager 2 has passed by these worlds. There remains much to learn. The major moons in order from the planet are Miranda, Ariel, Umbriel, Titania, and Oberon. 4 of these moons have known internal processes such as volcanism and surface canyon formation. Miranda is the smallest of Uranus's round moons and one of the smallest objects in the solar system to be spherical under its own gravity. Strangely, it also has the tallest cliffs in the solar system. Thought to consist of equal parts of rock and ice, Ariel's surface terrain, probably of ice, is cross-cut with canyons, scarps, and ridges. Umbriel is again thought to consist of rock and ice. Its surface is the darkest of the moons and heavily cratered. The surface seems to have gone through some form of surface heating that destroyed its very early features. Titania is the largest of Uranus's moons. Similar in composition, heavy cratering has been obscured by changes to the surface through some heating event like its sister Umbriel. Titania may have a tenuous atmosphere, as carbon dioxide and water ice have been detected on its surface. Oberon, the outermost of the spherical moons, seems similar to the others: ice and rock and heavily cratered. The surface has numerous scarps and graben from crustal movement. There are currently no plans to revisit these worlds. Neptune has 14 known moons, categorized into 2 groups, the regulars and the irregulars. The inner 7 moons orbit normally. The remaining half, including its largest moon Triton, orbit in either an eccentric, inclined, or retrograde motion. Triton orbits in the opposite direction to Neptune's spin. Scientists believe it was probably captured by Neptune's gravity in the early days of the solar system. Triton has an atmosphere that forms clouds and haze, and is the only moon closely observed by Voyager on its flyby of the system. However, Neptune plays a very important role at the edge of the solar system. The planets formed from a disk of dust surrounding our Sun billions of years ago. Remnants of this disk still remain: the rocky asteroid belt influenced by Jupiter and the icy debris cloud beyond Neptune.
Neptune creates a ring structure in the dust cloud which features a gap where the planet itself resides. And this gap should make it fairly easy to tell where Neptune is from afar, even at distances where the planet is too dim to detect directly. The supercomputer simulations that Mark Kushner and I performed also allow us to see what the dust in the solar system may have looked like when the solar system was much younger. In effect, we can go back in time and see how the distant view of the solar system may have changed. When we included collisions between dust particles, we were really amazed by what we saw. Dust collisions change Neptune's gravitational imprint. The gap in the ring structure disappears.
Over billions of years, Neptune shepherds the dust cloud into an outer ring to what is now called the Kuiper Belt. The New Horizons spacecraft is exploring this region with its first flyby of the enigmatic Pluto and its moon Charon. Charon is the largest of Pluto's 5 moons. The other 4 orbit in erratic motion around the Pluto-Charon pair. Nix and Hydra are both odd-shaped, contributing to their erratic orbital motions. This is Hydra, taken by New Horizons from a distance of nearly 650,000 kilometers, revealing its irregular shape. Pluto was the first of these trans-Neptunian objects detected and first thought to be a 9th planet.
And then Pluto was this kind of, odd guy out. It was this little object at the edge of the solar system. And then when we found all these other Kuiper Belt objects, this is kind of almost a third type of object.
So for the first time ever, we'll be able to fly by a brand new object, an object that's been forming for billions of years, and understand what outer parts of the solar system are all about.
Pluto is the first of the Kuiper Belt objects, or KBOs, to be seen up close. There are many other KBOs, or dwarf planets, awaiting detailed scrutiny, such as Eris, almost the size of Mercury, and Quaoar, the first KBO discovered. The most eccentric orbit belongs to Senda, which has an elliptical orbit of 11,000 years, taking it to the icy Oort cloud at the edge of the solar system. The Oort cloud will one day become the new frontier. Our solar system is vast. From our own star, the Sun, to Earth is nearly 150 million kilometers, or 1 astronomical unit. Jupiter is 5.2 AU distant, and Pluto up to 48 AU. And the solar system extends far beyond this into interstellar space. We humans cannot travel that sort of distance, at least not yet. But we can and do send our robots and probes in our place. And the results are astounding. The ion-propelled Dawn spacecraft is one of our emissaries that has rendezvoused with 2 asteroid belt objects in its multi-year mission.
The Dawn mission is one of NASA's Discovery Program missions that launched in September of 2007. So it's had a long, circuitous journey from the Earth, flying past Mars and out to the asteroid 4 Vesta, where it spent a year orbiting this small rocky object and mapped its surface and determined its bulk composition and geological aspects of Vesta before leaving the gravitational field of Vesta and traveling for another 3 years out to the dwarf planet Ceres.
Before the arrival of the spacecraft Dawn at Ceres, we were expecting an inert rocky body.
Instead, they discovered a world of mystery and surprise. Dawn has been orbiting Ceres for more than 2 years now, providing us with fascinating views of an alien world. The mysterious bright spots on Ceres appear to be salts deposited on the surface by subterranean activity. Support for this theory can be found in another feature of interest, the bright mountain named Ahuna Mons.
We have looking in detail about the shape of the mountain, and we have compared with what we know from volcanic constructs, and we have found that Ahuna Mons' shape is very similar to that of a volcanic dome that is built by very viscose material.
When we saw Ahuna Mons, we saw that its shape was very tall. It was very tall and had steep slopes. And that reminded us of certain places in the solar system, including Earth and Mars, that had domes that were formed by volcanic activity of very slow-moving, thick material. However, on Ceres, the temperatures are so cold that the same type of magma on Earth and Mars just can't exist on Ceres. So we then concluded that the magma, or the material that's flowing on Ceres, had to be composed of mostly very salty water that would flow at the low temperatures of Ceres. And when exposed to the surface, when they were pushed out onto the surface, they would freeze and form this steep-sided dome. Ahuna Mons is unique in the solar system. There's no other place in the solar system that has a structure that matches that of Ahuna Mons, and it has to be formed by cryovolcanic activity.
Scientists at the German Aerospace Center have used stereo images to create a global digital terrain map of the dwarf planet. Another surprise, a study published by lead author Norbert Schorghofer shows permanently shadowed regions at the North Pole. These are expected to be cold enough to accumulate water ice over long time spans. Future spacecraft visiting Ceres are likely to find freshwater ice there.
So right now we are not only learning about dwarf planet Ceres, but also about planets and small bodies in the outer solar system, like Pluto and its moon. And so we are in a phase in space exploration where we are learning about a new class of objects. And we are seeing that these objects are surprising, as they have recent features on their surface. These observations tell us Ceres was active in the recent past and might be even active today. And this tells us the importance of sending a spacecraft to a dwarf planet to have a close look at the surface, as we are learning new things that are unexpected.
Dawn is now orbiting only 386 kilometers above Ceres, which is closer than the space station is to Earth. And it will continue to return spectacular views. One of the key technologies that made Dawn such a success was its ion drive.
Ion propulsion allows us to undertake missions which would be impossible without it. There have been previous missions and tests of ion propulsion to validate the basic technology, but Dawn now has made it a reality. Dawn's the only spacecraft ever in more than 58 years of space exploration to orbit 2 extraterrestrial destinations, the last uncharted worlds in the inner solar system. And it not only allows us to get to these distant bodies, but once we're in orbit, we can maneuver extensively in order to get the best possible science that we can from the mission.
Our second deep space emissary has only recently arrived at its destination, the giant planet Jupiter. Juno is our fastest probe to date. Reaching a top speed of 265,000 kilometers an hour, or 73.6 kilometers a second, it has traveled for almost 5 years to reach its target and orbits the poles of the largest planet in the solar system.
Juno's the fastest spacecraft ever to venture into the outer solar system. It's the first to orbit pole to pole about Jupiter, and it's the most heavily shielded spacecraft that we've ever launched. The mission is designed to basically wrap Jupiter in a dense net of observations, completely covering the sphere. So to do that, we need a polar orbit, one that passes over the North Pole, along a line of longitude, and over the South Pole. And we do this over the 37 orbits of the nominal mission, and by the time we're done, we've got orbits separated in longitude by about every 12 degrees. So we completely cover the sphere.
Basically, the interior of Jupiter is nearly unexplored. What we see when we look at Jupiter and all the great, amazing stuff we've discovered about Jupiter is about the moons that orbit the planet. It's about the atmosphere and the enormous weather systems and the great red spot and belts and zones, stripes across the planet, all kinds of really cool, interesting, exciting stuff, but it's kind of skin deep. When we look at Jupiter, we're going, 1% or 2% of the way down into the planet. That's what we're really seeing. Everything else about Jupiter, the deep interior of Jupiter, is nearly completely unknown.
To peer beyond the veil, the suite of instruments on board Juno includes a gravity radio science system, plasma and energetic particle detectors, ultraviolet and infrared spectrometers, and a vector magnetometer.
A magnetometer is, it's best to think of it as a fancy compass. Unlike a compass that just records the direction of the magnetic field, our instrument tells you both what direction the field is in and what the magnitude is. And we can measure that very, very accurately to 100 parts per million. Juno's magnetometer is another in a long line of magnetometers built here at Goddard Space Flight Center, following designs developed by Mario Cunha years ago. Our instrument is between 1 and 2 orders of magnitude more accurate than anything that's flown to Jupiter before. And of course, part of that is the result of the star cameras that we're able to fly with our sensors so that we can determine the absolute orientation in space of these sensors. If we did not know the orientation of the sensor as well as we can determine it with the star cameras, we would lose accuracy in the vector measurement. So we carry 4 star cameras with our 2 magnetometer sensors. These have to be held in the same orientation with respect to each other under very extreme environmental conditions. So we designed what we call a magnetometer optical bench. It's a special structure, about a square foot in size, that is made of a carbon silicon carbide material, almost impossible to machine. But once it's fabricated and the sensors are assembled, they act as one. And that's one of the reasons why we can achieve much higher accuracy than has ever been attempted before.
Studying the magnetosphere of Jupiter is a prime objective.
Magnetic fields have been a curiosity for thousands of years. And so, of course, we know now that magnetic fields are generated by what's called dynamo action, the convective motion of an electrically conducting fluid. Even though we can map the Earth's magnetic field with extraordinary accuracy with satellites in orbit about the Earth, the one thing we can't do is see clearly through all the crustal magnetization that is right beneath our feet. Jupiter is a gaseous planet, hydrogen, helium. There is no magnetized crust that obscures our view of the dynamo deep below. So the exciting part about the Jupiter mission is that we'll be able to image for the first time the magnetic field on the dynamo surface in a way that would never ever be possible on Earth. Jupiter is also the planet with the largest magnetic field. Its magnetosphere is huge. If you were to look up into the night sky, and if you could see the outline of its magnetosphere, which you can't, it would be about the size of the moon in the sky. It's a very, very large magnetosphere. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the sun, extends all the way out to the orbit of Saturn and in all likelihood beyond. It's a very large feature in our solar system. It's a pity we can't see it.
Of course, a strong magnetic field traps more radiation within its grasp, another issue for Juno.
There's 2 types of radiation we worry about. One is when we fly through the radiation belt, we get an instantaneous exposure, we call that flux. The other is flying through the radiation belt again and again and again gives us something about accumulation, we call that dose. And so in the beginning of the mission, we fly largely close to the planet underneath this kind of flat donut-shaped radiation belt, and then we fly around it. But eventually we fly more and more through the belts, and our radiation levels, every orbit, get worse and worse and worse. We get over 80% of radiation exposure in the last half of the mission.
For me, the great excitement is the opportunity to look down and get the first clear, unobstructed view of what the magnetic field looks like on the surface of a dynamo where it's generated. It's always incredible to be the first person in the world to see anything. We stand to be the first to be able to look down upon the dynamo and see it clearly for the first time.
Our emissary to the ringed planet Saturn is now in its final year of operation. Its outstanding performance has included dropping a probe on the moon Titan, making extensive observations of Saturn and its moons, even adjusting its mission to fly through the water vapor plumes discovered gushing into space from the moon Enceladus.
Cassini was never designed to look for life in the Enceladus ocean, But it does have powerful instruments that can be used to look for habitability. So we're looking for the conditions suitable for life. Now Enceladus is a tiny moon, but it's really intriguing. It's got this plume that is shooting out from its south pole. The plume's mostly comprised of water ice, that gets frozen when it's ejected out into space. Most of these particles are coming from these 4 major fractures that we call tiger stripes. Life needs 3 things, right? It needs water, it needs chemistry, and it needs energy. And right now, some of these lines of evidence are telling us that Enceladus has these 3 things. We see some salts, but most importantly, we see organic molecules, things like methane. We also see CO2, ammonia. One of the things that Cassini can look for is molecular hydrogen. This is the smallest molecule that exists in the universe. It's 2 hydrogens bonded together. This molecule can tell us about things like hydrothermal activity going on in the ocean of Enceladus. And this is very important as we start to answer that ultimate question of, is there really life on Enceladus?
NASA's Cassini mission has begun a daring set of ring-grazing orbits, skimming past the outside edge of Saturn's main rings. Cassini is flying closer to them than it has since its arrival over 12 years ago. It will begin the closest study of the rings and offer unprecedented views of moons orbiting near them. Even more dramatic orbits will take Cassini through the F ring, the outer and most active ring, which contains 1 ring and a spiral strand around it. Cassini will make its final orbit later this year and plunge into the Saturnian atmosphere, ending more than 11 years of scientific observations. Traveling over 10 years and 5.5 billion kilometers, New Horizons is our emissary to the outskirts of the solar system. In a dramatic flyby, New Horizons scanned Pluto and its main moon Charon. The brief encounter amassed gigabytes of data, which the spacecraft took months to download to Earth. Its close-up details of Pluto's terrain generated a great many questions. It looks more complex and highly active geologically than first thought, with solid nitrogen ice forming many fascinating and colourful textures and landscapes. New Horizons captured this high-resolution enhanced colour view of Charon just before closest approach. Charon's colour palette is not as diverse as Pluto's. Most striking is the reddish North Polar region, informally named Maunder Macula. After such a successful flyby, the mission has extended to include a second Kuiper Belt encounter. New Horizons is set to fly past 2014 MU-69, a Kuiper Belt object currently about 1.6 billion kilometers beyond Pluto. Arrival time, January 2019. As one mission ends, another is about to begin. Bepi Colombo, Europe's first mission to Mercury, is currently being put through its paces at ESA's European Space Research and Technology Centre in the Netherlands. Bepi Colombo consists of several components in a so-called spacecraft stack. Apart from the two orbiters, there's also the Mercury transfer module, which contains the solar electric propulsion engine to get them there.
Okay, what we have here is the MTM, the Mercury transfer module, which brings us, or our two spacecraft, to Mercury, the 3 xenon tanks, and the 4 thrusters. And when we arrive at Mercury, this unit will be jettisoned, and then we only have our 2 spacecraft.
The 2 spacecraft are ESA's Bepi Colombo and the JAXA magnetospheric orbiter. Mercury is the closest planet to the Sun in our solar system. Yet despite temperatures reaching around 500 degrees Celsius, the previous NASA Messenger mission found evidence for ice at the planet's north pole.
One spacecraft is provided by ESA, which is MPO, we call it MPO, Mercury Planetary Orbiter. And this spacecraft has a focus more on the planet. We want to observe the planet, do remote sensing, characterize the surface, count the craters, wanting to know about the composition of the surface, the interior of that planet. And in addition, we have a second spacecraft, and this spacecraft is called the Mercury Magnetospheric Orbiter, more focused on the environment, and this spacecraft is provided by the Japanese Space Agency.
The Messenger mission found other surprises at the smallest planet in our solar system. It discovered more chemical elements and compounds with small boiling points, known as volatiles, than expected at the surface. Messenger focused on the north polar region, whereas Bepi Colombo and its instruments will cover the whole planet, as well as exploring its gravity field.
One of the special things about Mercury is that it's the only planet besides Earth who has a magnetic dipole field. And so we would like to understand the dipole around Mercury, or how the magnetic field around Mercury is interacting with the Sun. And that's very important for us, because then we can learn for Earth how the Earth's magnetic field is interacting with the Sun. And we have a lot of satellites around Earth which are affected by the solar wind and the interaction. So if we can get some clues about processes on Mercury, we want to learn for Earth.
Bepi Colombo's launch has been set back by minor hardware issues. Now scheduled for late 2018 launch, it is expected to reach Mercury in 2025. With the go-ahead from NASA, the Europa Clipper mission is underway, with the selection of instruments to fly on the spacecraft hopefully in the early 2020s. Its mission is focused on the Jovian moon Europa, believed to hold an enormous ocean of water beneath its icy surface. Europa's proximity to Jupiter and its speedy orbit cause the moon to stretch and contract under gravitational forces, generating mechanical heat within the core and providing enough energy to maintain a liquid ocean. Close inspection of surface areas also predicts that ice movement on the surface, similar to glacial movements, could allow for the formation of liquid water lakes close to the surface. One more place to search for those elusive signs of life. For over 50 years, we have bombarded Mars with our probes and landers, spying from orbit to map the terrain, finding her strengths and weaknesses. On the surface, probing for her resources and learning of her defenses. The next generation of robots are readying to establish the beachhead. The time is approaching for the full-scale invasion of the planet, when humans walk on Mars and claim it for their own. The conquest of this enigmatic planet so far away has been both challenging and rewarding. ESA has delivered the latest conspirator, the ExoMars Trace Gas Orbiter, to search out the source of methane in the atmosphere. Its landing craft, the Schiaparelli lander, failed and crashed, yet another victim of Mars's defenses. The ExoMars orbiter, now captured by Mars's gravity, has begun the challenging process of adjusting to a circular orbit without fuel. This involved using the shifting Martian atmosphere to gradually slow the satellite in a process known as aerobraking.
With ExoMars, ESA is going to use for the first time a method called aerobraking for a spacecraft in orbit around Mars to decrease the orbit by letting it fly through the atmosphere and using the atmospheric density to slow it down instead of using fuel for the engines.
We have to take a lot of margin to be sure that even if we go through a moment where the atmosphere is more dense at the altitude where we are flying, we are still safe with the spacecraft.
That aerobraking process took more than a year to complete. It was complicated by the changing nature of the Martian atmosphere.
The Trace Gas Orbiter is really looking at active processes ongoing on Mars today, and life, present life, is one of the possible explanations. So it will be really a Sherlock Holmes work to try to put together a case for whether it's geological or biological activity that is responsible for the methane.
Meanwhile, plans are well advanced for the ExoMars 2020 mission, with the final design of the rover nearing completion. And scientists have shortlisted two possible landing sites to put it to use: Oxia Planum and Morth Vallis. Both are shortlisted because they have had an abundance of water in the planet's early history, the main building block for life.
First of all, we want a landing site that is ancient, because the hypothesis is that conditions on the surface of Mars 4.3 to 3.9 billion years ago were similar to those on Earth when life started here. So the site has to be old. The second condition is we want a site where we had liquid water present over hundreds of millions of years. And we want this liquid water to be what we call low energy or slow flowing water, like on the canals in Amsterdam.
The rover then scouts around for the ideal locations and, with its driller apparatus, digs deep into the Earth to extract soil samples, which will be placed into its onboard chemical analysis equipment, hoping to find ancient signs of life. Beginning this year, the next wave of spacecraft begin their sojourn to the Red Planet. NASA's InSight mission, the first to be launched from Vandenberg Air Force Base in California for another planet, is preparing for liftoff. The vehicle had already been through its pre-flight test and had been shipped to the launch facility. It is crucial that all aspects of the lander are in perfect operational readiness. The probe is destined for the equatorial region of Mars and will look deep into the heart of the planet.
The InSight mission is a geophysical mission to Mars. It's going to go to Mars and take its vital signs. It's going to take its heartbeat, the seismic activity of the planet.
So we're going to be doing that using a seismometer, a very high precision seismometer, using techniques that have been well developed on Earth to get the understanding of the crust, mantle, and core, and sort of the relationship between those.
Going to take its temperature by measuring the thermal gradient of the surface, which tells how much heat is coming out.
We also have a heat flow probe, we call it HP cubed, and what that does is it's going to basically take the temperature of Mars, and from that it'll be able to understand what the thermal flux is over the course of a full Martian year.
And it's going to sort of measure its reflexes by looking at how the rotation wobbles with the tidal effects of the sun.
Our final experiment is called RISE, and that's going to be looking at basically the wobble of Mars to help understand what the core size may be and composition.
InSight isn't just a Mars mission, it's really a mission to the terrestrial planet interiors.
So Mars is kind of the Goldilocks planets. It's not too big, it's not too small, it's just right. If it was too big, it would have retained a lot of activity and erased all the evidence that we're looking for. If it was too small, it never would have undergone the same processes that formed the Earth, and so it's really just right.
Mars will give us this insight into early planet formation and early planetary processes.
Understanding the details of the structure of the interior of Mars will allow us to address questions of planetary formation that we've only been able to guess at before.
We are missing cold, hard data, and this is what this mission will provide.
Meanwhile, NASA, ESA, and the Russians are continuing their programs. Soon, new missions from China, Japan, India, and the United Arab Emirates will begin. Getting humans to Mars is the pressing goal of NASA and other adventurous parties. Many big aerospace corporations contractors have all been at the drawing board working out the immense engineering and logistical challenges. They all concur that to get to Mars, you need more than a big rocket. NASA's SLS and Orion spacecraft are only two of many components that will be needed. With some more political emphasis, NASA, in concert with other agencies including ESA, Canada and the Russian space agencies, are able to push ahead with the Gateway Facility concept. Effectively building a space station in cislunar orbit between the Moon and Earth, it would be a staging post for a return to the Moon, the gathering of resources from the lunar surface, and an assembly point for a Mars flight and beyond. Orbital ATK is one of 6 companies selected for NASA's Next Step 2 program, a public-private partnership for commercial development of deep space exploration. Not the first to suggest the Moon be a staging post, Orbital ATK recommends a parking orbit in cislunar space built from its successful Cygnus cargo craft. First, they will launch an initial habitat module aboard NASA's heavy-lift SLS rocket with a crewed Orion capsule. Placed in a parking orbit, it will act as a platform for experiments and serve as a destination for future crewed missions. By 2025, additional modules would be added to the habitat, allowing deliveries of crew supplies and experiments, and serve as a waste disposal vehicle at the end of their missions. The modularity of the system also allows for multiple visiting vehicles, providing a base for lunar sorties. Mining for resources, in particular water, would allow for more cost-effective and longer duration missions to Mars. From water you gain hydrogen for fuel, oxygen as the oxidizer, and for breathing, and of course, drinking water.
We have places on Moon which are, at least especially at the South Pole, which has permanent darkness, where we can find water, and we know from some missions that there is water. Water is a good source to produce hydrogen and oxygen. And also to go into the shadow of the Moon, we will have places where we don't have the radiation coming from the Earth. So building a telescope over there by using the material we find on the Moon, so not bringing all the stuff from the Earth, that could also open new possibilities to look deep into our universe.
These crewed missions would also help with man's understanding of how we can best survive long-duration space exploration. By 2030, with additional modules, the habitat could be expanded to provide a Mars transit capability for demonstration expeditions lasting 1,000 days or more. Boeing, the primary contractor for the SLS rocket system, believe their plan will require 5 or 6 SLS launches to be able to get to Mars.
So we want to make sure that we've checked everything out and that we know that it's good to go before we actually leave for Mars. Because once we leave, we can't come back for over 2 years. And the reason for this is because it's the alignment of the planets. The way the planets revolve around the sun, it allows a window of opportunity to go from Earth to Mars basically every 2 years. Just to get to Mars, before you even land or anything, is going to take 7 or 8 months. The reality is you're going to be there for a year waiting until that window opens up and come back. And then it's going to take 7 or 8 months to come home.
Having a cislunar outpost enables international partnerships and commercial opportunities, such as exploration of the lunar surface and scientific and technological research. After cislunar space, we'll start the actual missions to Mars. The first mission will be to Mars orbit. This mission will teach us about the space systems that will take us to Mars and back. The next mission will send humans to the surface of Mars. The crews will undertake detailed scientific research and investigation. They will start to unlock the secrets of Mars.
Their initial concept, now under development, consists of a power and propulsion bus to provide electric power and propulsion, 2 habitat modules, an airlock module, and a logistic work module, then supplied by cargo and crewed modules from the US and Russia. And finally, it could be used as the vehicle and habitat for long-term exploration of space. Lockheed Martin's concept for transporting to Mars has resulted in a holistic view of the mission. They too will assemble the space gateway in cislunar orbit. This will provide the platform to build the Mars Space Base Camp and get it ready for flights to Mars. They see that Orion is a part of a larger system that provides the supplies and the scientific equipment needed for the journey. This resulted in what they are calling Mars Base Camp. Mars Base Camp is an orbiting mission with 4 main sections and 2 of almost everything for backup. Four large commercial solar arrays to generate electricity to power the spacecraft. For propulsion, we have 2 cryogenic stages, one either end, and 2 tank farms to store the fuel and oxidizer. Within those stacks lie 2 habitat modules and a large central living space to eat, sleep, and exercise. Most importantly, we have Orion. It is the command deck with all the avionics, navigation, and communications. Orion makes the spacecraft more reliable and gives the astronauts a safe ride home. The orbiting crew could also investigate the 2 moons of Mars, Phobos and Deimos, deploying landers or robots for sampling, even astronauts to explore the surfaces of these moons. The main mission, however, will, after careful examination, confirm a landing site for the next mission and the first human landing. From orbit, the astronaut scientists will have access to the entire planet's surface for rovers and drones to be able to make real-time decisions about where to go and what to examine, retrieving samples from the surface for study. Lockheed Martin's concept, the almost retro rocket ship, the MEDV Lander, is their design for a reusable launch and landing vehicle and is based on the current technology, including the Orion and shuttle systems, and not as far-fetched as first thought. Reusability and innovation will conquer Mars. Keeping costs down will make it viable, and making it doable is innovation. That's something that SpaceX is founded on. Their BFR is the direct Mars transport system, from liftoff on a reusable booster, a short time parked in low Earth orbit for a fuel top-up, then direct to Mars and a 3-month cruise, then landing directly on the surface of the red planet, ready to be refueled from local resources for the return journey, landing back on Earth in the one reusable spacecraft. In the meantime, SpaceX is testing its Falcon heavy rocket system in preparation for its maiden voyage. One of the issues of flights to Mars, which is addressed in part by the BFR, is the cruise time. In theory, SpaceX has it down to 3 months. The other NASA-led systems will take 7 to 8 months, a long time to house, feed and power a crew with little to do. Getting there much faster would be a game changer. One possible way to achieve this is nuclear power. Nuclear thermal propulsion, or NTP, could enable faster transit time both to Mars and beyond. NTP is powered by nuclear fission. How it works is conceptually simple. Energy from fission is used to heat a hydrogen propellant to about 2,420 degrees Celsius. This hydrogen is then accelerated through an exhaust nozzle, resulting in a propellant efficiency roughly twice that of the best chemical rocket engines. For example, it may be possible to fuel modern NTP systems with low-enriched uranium instead of highly enriched. The physical size of an NTP engine is largely determined by the rate at which fission energy can be transferred to the hydrogen propellant, but the equivalent volume of the uranium that would be split is actually quite small, roughly that of a toy marble. Getting travelers to Mars faster, NTP can take months off the trip compared to using traditional chemical systems. This would reduce the need for payload, food and power for the crew, minimizing the risks associated with exposure to galactic cosmic radiation, microgravity, and other hazards of deep space travel. The maturation of nuclear thermal propulsion will also promote the successful development of the kilopower fission power systems for use on the Moon, Mars and other destinations, as a main source in situ for life support, communication, industrial and other diverse applications. Harnessing first-generation NTP systems is a first step towards advanced nuclear propulsion systems capable of travel throughout the solar system. The amazing Cassini spacecraft and its sibling lander Huygens have now concluded their scientific studies, bringing back years of data to be combed through by scientists, plotting their next journey to Saturn's space. Now it's time for other planets and other spacecraft to shine. Juno piercing the cloak of Jupiter, and her distant relative New Horizons at the edge of the solar system. After 20 years, the Cassini project finally comes to an end in dramatic style. But with one door closing, another opens. Now the enviable task of having to unravel the data Saturn has just laid bare begins. And they have literally just scratched the surface.
I think Cassini has left us with humankind's presence at another planet for 13 years, seeing things that we had never imagined seeing, and at the same time sharing that with the entire world and opening up vistas for the next sets of missions.
One of the issues facing scientists when looking at exploring the new frontier is leaving it in a better state than they found it. So eliminating the problems of space junk or the introduction of alien microbes is paramount in their decision-making.
But it also helps us satisfy a planetary protection requirement. We're protecting the tiny moon Enceladus as well as Titan. Both of those have global oceans underneath their icy crusts, and just in case there might be life in those oceans, we don't want Cassini to crash into one of those moons once we're out of fuel.
While the main focus of the Cassini mission was to delve into the mysteries of Saturn and its rings, the moons of Saturn proved most science-worthy. And Saturn has many moons. In fact, 62 with confirmed orbits. Several are only 50 kilometers in diameter, the largest being Titan, which is bigger than Mercury. The Huygens module that traveled aboard Cassini also became the first probe to land on a moon other than our own and transmit data back to Earth.
The temperature at the surface of Titan is about minus 180 degrees, so it's very cold. The landscapes of Titan look a lot like those we have on Earth. We have rivers, lakes, seas, almost oceans of methane. It rains methane or a mix of ethane and methane, so there are lots of meteorological phenomena or geophysical phenomena on Titan that makes you think of what happens on Earth. But the ingredients are quite different.
But it is Saturn's sixth largest moon that excited many scientists, as it is virtually covered by clean ice and ejected plumes of water into space.
My favourite moon is Enceladus, and the reason I'm partial to Enceladus is it's the moon that my team discovered a water vapor plume at. But not only is there liquid water underneath the surface, but there's organic material, there's a heat source. You know, when people get excited about the potential for life elsewhere in the solar system, there are four things that you need. You need a heat source, you need liquid water, you need organic material, and you need those three things to be stable over some period of time so that life could potentially form. At Enceladus, we've got three. We're not sure about the stability over time yet. And so based on the Cassini observations we made back in 2005, we've had lots and lots more flybys of Enceladus. We now understand it much better. We understand what organic material is there. I mean, one of the instruments, the ion neutral mass spectrometer, in a very close flyby through the plume, found some ammonia in the plume.
First of all, we see plumes. Then we start finding out from the gravity measurements and the imaging that there's an ocean and that it's global. And then there was some measurements by the cosmic dust analyzer that suggested there was hot water being circulated through the rock, the silicon dioxide nanoparticles. This is just the final step that shows that there's molecular hydrogen being produced by these same hydrothermal processes, and that molecular hydrogen has the chemical energy to support microbial systems in the interior ocean.
It's really the longevity of the Cassini mission that's allowed us to put together the pieces of the puzzle to really understand a moon like Enceladus. And even this late in the mission, we continue to look at our data to better understand this ocean world.
Collating data is one thing, but interpreting and providing vision for future missions is another. This is an area for which the Cassini project came up trumps, because it not only brought together 3 agencies, it provided the ground for future scientists to develop skills that will provide the basis for new projects.
The number of PhDs we've put through the system that are going to be the educators of the next generations. We've put out 3,000 plus peer-reviewed papers, hundreds of PhDs, thousands of peer-reviewed papers. The legacy, the scientific legacy is huge. The engineering legacy, of using every ounce of engineering capability to exploit a system, I think is again, we will be built upon. And I can't ignore the international cooperation. I mean, we had 19 nations contributing hardware to this mission. We've got over 26 nations now contributing scientifically.
The mighty Jupiter is the current target under the microscope with the Juno mission in full swing. The story of our solar system is linked to Jupiter, as it is believed that it was the first planet formed. So if we can understand how, we can begin to unravel the origins of our solar system, and thus how the Earth came about. Juno must work in a very harsh environment to tease out the answers from the gas giant.
When you go to a place as hazardous as Jupiter, we put a lot of time through the whole development process and trying to design a spacecraft that will operate in the high radiation fields, the magnetic environment, the spacecraft charging environment, everything that you deal with at Jupiter. And I have to say the spacecraft has been performing admirably.
Jupiter's radiation belts pose one of the biggest problems faced by Juno scientists. They exist within the enormous magnetic field that surrounds Jupiter, with its magnetosphere trapping and accelerating particles. It produces intense belts of radiation similar to Earth's Van Allen belts, but thousands of times stronger.
Juno just flew by Jupiter for the first time with all the science instruments on, and it was spectacular. The spacecraft performed flawlessly, the instruments all worked exactly as planned, and the data is amazing. We're looking deep into Jupiter, we're learning about the secrets that it's holding, but we're also getting a lot of surprises about the aurora, about the atmosphere, how it works. I mean, it's just incredible.
The flybys which followed showed that the massive amounts of energy swirling over Jupiter's polar regions were creating the giant planet's powerful auroras, but not in ways the researchers expected. What puzzled the researchers was the fact that despite the magnitude of these potentials at Jupiter, they are observed only sometimes, and are not the source of the most intense auroras as they are on Earth.
Juno had its camera, JunoCam, on during the flyby. We got the first pictures of Jupiter's poles, the North and South Pole. They were amazing, a lot of surprises. It didn't look like we thought. Doesn't look much like Saturn's pole.
Jupiter's poles are covered in these cyclones and anticyclone storms, some of them half the size of the Earth or bigger. And we're puzzled as to how they could be formed and stable in that configuration. And the North Pole doesn't look like the South Pole. And so we're questioning, the scientists are really questioning whether this is a dynamic system and are we seeing just one stage and over the next year we're going to watch it disappear? Or is this a stable configuration and that these storms are circulating around each other?
While the polar activity appears unique to our solar system, the engineers are looking below its shell for answers.
The new science results from Juno really are our first look at close-up at how Jupiter works. And so the first time we're looking inside of Jupiter with into the interior, and what we're seeing is that it doesn't work at all like we had predicted. Almost every model that has the interior motion, how the magnetic field, the gravity field, how the deep atmosphere works, it's all different.
Like most scientific undertakings, they result in more questions being asked than answered.
So Juno's original objectives really were to understand how Jupiter formed, and that would help us understand how planets general form and how the whole solar system was made. What we're finding is that actually we didn't understand giant planet dynamics very well, the whole atmosphere or interior structure.
What we've seen so far is exciting, no question about that. But it's like a puzzle, and we're putting the pieces of the puzzle together, and it's exciting, but we don't have the whole picture yet.
And one of those puzzles is the so-called Great Red Spot. And while its presence in a turbulent gaseous planet is not unusual, the scale is. The red spot covers an area twice as large as Earth.
And we're going to go right over the Great Red Spot. And that's really going to be the first time that we get a close look at that and to see what it's like underneath the top surface layer. I mean, how deep are the roots to that? That's a 300-year-old storm. A lot of scientists believe that the roots must be very deep. Well, when we go over with our microwave radiometer, we're going to see, is it the same as the zones and belts, or is it very different? And nobody really knows.
But it's not just Jupiter's poles that hold the greatest interest for the Juno investigators. They are also intrigued by the weather pattern that is unique to this planet, yet familiar in other ways. Studying the atmospheric dynamics helps understand other planets' atmospheres.
So when we look at Jupiter, we see a lot of structure that looks very similar to the Earth. We can see storms, we see cyclones, we see anticyclones, and these sort of storms and weather systems that we see on Earth are very similar, and they're happening on Jupiter. Fluid mechanics is hopefully the same everywhere in the universe, but Jupiter and Earth are very different. Jupiter is much bigger, it rotates a lot faster, they're made of different material, and Jupiter's much further away from the sun than the Earth is. The quasi-biennial oscillation, or the QBO, on Earth is an equatorial phenomenon in the stratosphere where the winds are changing direction approximately every 2 years. Depending on which phase the QBO is in, eastward or westward, the temperature signal corresponds to that. So it's warmer in the eastward phase and cooler in the westward phase. It's been shown that it can actually be a barrier to transport of aerosols across the equator and has been linked to the frequency and the formation of hurricanes in the Atlantic and the Pacific Ocean. The long-term scales on Earth's climate is something that we're very interested in, and how that applies to other planets' atmospheres is really why we're studying Earth and Jupiter. The quasi-quadrennial oscillation in Jupiter's stratosphere is a temperature signal that we see in the equator, where we see the temperature get warmer and cooler approximately every 4 Earth years. We used a general circulation model where we focused on simulating the effects of small-scale waves produced from convection in Jupiter's equatorial region to simulate the QQO. The waves propagate upwards from the clouds and force the winds in the stratosphere to change direction, going from eastward to westward approximately every 4 years. Our model was able to reproduce the behavior of the QQO, but was also able to reproduce temperatures from the observations, and both of those together give us a lot of confidence that our model is very accurate in what's driving the QQO. The outer planets serve as a laboratory for understanding atmospheric physics under very different conditions that are present on the Earth. Understanding how their atmospheres change and evolve and their climates can give us insight into any planetary atmosphere.
Juno has studied the planet with a suite of tools revealing much that was previously hidden to the human eye.
We have an infrared instrument on Juno called JURAM, and it was designed and built and delivered by the Italian Space Agency. And this instrument makes thermal maps of Jupiter. So the images are showing you what's warm, hot, cold on Jupiter. And one of the things you can see right away is the center of some of these hurricane-like storms are cooler than the surrounding area. And sometimes you go over a warm spot. And we went over one that was very small that seems hotter than the surrounding area. And that's very similar to what the Galileo probe went into back in 1995.
The Juno mission is unique because it's the first time that we've ever gone in a polar orbit, which goes from pole to pole, over the North Pole, through periapsis, and under the South Pole. All the other missions we've done and all the observations we made from Earth were made from the equator. And you don't see the poles very well if you're sitting on the equator. Yes, this is the first time we get the first clear, unobstructed view of what the aurora looks like and what the polar phenomena looks like. And at the same time, we're flying through the magnetosphere right above the aurora so we can sample in situ the charged particles that are precipitating down magnetic field lines, the guys that are exciting the emissions that we see.
Juno, like its sister Cassini, has a use-by date when the craft runs out of maneuvering fuel. This may occur during its 12th orbit at the end of its prime mission. However, NASA may choose to extend the mission if there are sufficient reserves. In that case, the deorbit would occur later, on the 34th orbit, as part of the planetary protection policy of NASA. Its pathfinding mission is leading the way for the one to come, the Europa Clipper, a mission in the design phase to look closely at Europa, the moon with a hidden ocean, and the possible location for life to evolve beyond Earth. The blue haze of Pluto's atmosphere, possibly a hydrocarbon smog, seen from 200,000 kilometers away by NASA's departing New Horizons spacecraft. A few years ago, the dwarf planet Pluto and its 5 known moons were just small dots in the outer reaches of our solar system.
One of the important things you should understand about Pluto is the real scale of it compared to the rest of the solar system. So we've come to the beach to really convey that scale and distance. So if I draw the sun as a 30-centimeter circle, then we have to walk about 35 steps this way in order to draw the Earth in the same type of scale. So we're walking the equivalent of 150 million kilometers, which we call 1 astronomical unit. Normally, Pluto orbits at about 40 astronomical units from the Sun, but it's actually quite an elliptical orbit, so it changes between about 30 and 50 astronomical units. But back to the Earth. So the Sun is over there at 30 centimeters, which means that the Earth should be about here, about 3 millimeters, something like this. If we were to draw Pluto in the same scale, it should be 0.3 millimeters, and it should be 1 kilometer down the beach. So I'm going to draw it. Now obviously I can't draw something that's 0.3 millimeters, so I have to draw Pluto a bit bigger. If this is Pluto, then its largest moon is Charon, which is about half its size. But Pluto has 4 other moons: Styx, Nix, Kerberos, and Hydra. So there's a lot going on around the Pluto system. It's not just a cold, dead, icy rock.
The spacecraft spent 16 months sending its data back to Earth, and scientists and non-scientists alike have been enthralled by what it has revealed.
If you go in closer to the surface, you can see this type of really diverse terrain. So you have a very bright region. These are flat plains. I'm not entirely sure how they formed yet, but there's a couple of leading theories. There's a huge range of mountains. There's all kinds of different aged surfaces. Some of them have lots of craters. Some of them have very few, which means they're younger. If you look at in a lot of detail at some of the mountainous regions, you can see that actually they're a few kilometers high, but they're made of water ice. I mean, that's on Pluto, it's so cold that water ice is the hardest thing. It's more like rock. And so the stuff that forms the softer material is actually nitrogen ice.
Water ice on Earth is close to 0 degrees, but on Pluto, it's minus 230 degrees Celsius. And there's a glacier of nitrogen ice, called Sputnik Planitia, thought to be under 1 million years old. This is young by planetary standards, and no one knows yet how it formed or is renewed.
One of the really fascinating things is some of the surface coloration you can see in these images actually shows that there are these compounds called tholins, which are a combination of elements, but they're related to prebiotic molecules, so they're kind of relevant to prebiotic chemistry. And I think the fact that they have been able to form on planetary surfaces very far out in the solar system at very cold temperatures really has implications for a lot of places. I mean, if you can imagine for star systems outside our own, where the star may be dim and the planets are quite far away, it's interesting to know that there are molecules that could be involved in supplying biotic material to processes that may one day lead to life or be involved in life or something like that. That they're actually forming way out in the solar system where no one really expected.
Pluto is unlike anything seen before. But the 6 gigabytes of New Horizons images and scientific measurements are giving scientists mysteries to unravel for years to come. In the meantime, asleep for the moment, the probe travels deeper into the unknown, soon to awaken at its next destination.